Welcome to LECCE and welcome to the University of Salento. The University of Salento is the university of the two seas, the Adriatic Sea and the Ionian Sea. And we will have time also to enjoy during the coast, during this week. This is the fourth edition of this International Radiocarbon Conference. After the first one in Belfast in 2014, the second one in Hungary, Debrecen, in 2017, and the third one in remote due to the COVID pandemic in Gliwice in Poland. And here we are in Lecce, in the castle Charles V, and we thank the director and the authorities that allowed us to stay here. And I want to thank you very much because we know that in less than 1 month, most of us will be in China for the MS-16 conference. And I know that you came for a long distance. Maybe you will suffer for a few days about the jet lag, but we would like to have a very exciting conference, a lively concert. So please, you are not allowed to sleep a little bit, and we will do all the best to do that. Nessun dorma means no one falls asleep, thanks to this famous opera, Italian opera by Puccini. And this is the second important conference organized by the Applied Physics group of this university. After the first one, you remember, in Rome, it was 2008 that we organized in collaboration with our colleagues from Caserta, Firenze, and Trieste. And we are very glad to organize this, which is the second important conference of our community. In 1999, the rector of this university gave me an important task: to realize the first Italian center for research and service about radiocarbon dating by accelerator mass spectrometry. At that time, I didn't have the vaguest idea what MS was and not even radiocarbon. So I went around looking for collaborations, and I received some help in France from the CNRS in Gif-sur-Yvette and the Tandetron laboratory. And for the sample preparation, a lot of help was done to the Leibniz lab of the University of Kiel in Germany, and also the ETH in Zurich in Switzerland. So we start our big project. Nothing was there, empty spaces, no technologies, no people. It was 25 years ago. And now CEDAD, the Center of Data and Diagnostic, has a lot of technologies, many laboratories, 4 ion beam analysis beam lines and 2 AMS beam lines, one dedicated to radiocarbon. We have 10 laboratories: the chemical laboratories for accelerator mass spectrometry, the chemical laboratory for isotope analysis, and many others, even electron microscopy with a very high atomic resolution, 63 PM picometers, and 2 research infrastructures known as ACTRIS and Bio Open Lab at the Department of Mathematics and Physics of this university. And the research area spans from biomedical sciences, cultural heritage, environment, and so on. And last week we went in Holland at high voltage because we will have soon a second accelerator, which will be a new accelerator, compact, small, new generation for biomedical applications. It is manufactured by High Voltage Engineering Europe. And I remember my first conference in this field. It was 1999 in Vienna, organized by the Vera Laboratory and Professor Kutscher. And I remember that I had a strong headache for the whole week, I didn't understand nothing. I thought, I'm in the wrong place. It's not possible. We will fail with this project. And Walter was in 1999 exactly like you see him today. Young, timeless, very active. Today is as it was 25 years ago. But unfortunately, today, I'm 25 years older than in 1999. This is a quite funny introduction. You know, we have to go fast because we have to go to China. We received a lot of abstract posters, presentations, and we have to move to see the laboratories. We have to go to Gallipoli on Wednesday. So we have to fly, I should say. We have to volare, we say in Italy. Volare means to fly. On the other hand, cosmic rays fly in the intergalactic spaces to produce neutrons that then interact with the nitrogen-14, forming C14. And C14 oxidizes, as we know, and forms CO2, and flies in the atmosphere, mixing everywhere. Volare. This is the leitmotif also of this conference.
Volare. Cantare, nel blu dipinto di blu, felice di stare lassù.
And it's written also on the back of your badge, you know, volare ho ho, cantare o o o o. This is the leitmotif, the very maybe the most famous Italian song by Domenico Modugno. Anyway, he was born very close to Lecce, in Polignano a Mare, another beautiful place to visit. But we want to like to give you just a taste also of the Italian style of this part of Italy. You know, Italy has a form of a boot, and you are very close to the heel of the boot. Many archaeological sites, Baroque-style buildings, and so on, and also popular beliefs. One of these is related to an insect, a kind of spider. It's called tarantula. Be careful, because tarantula is everywhere, especially in a place like this, a castle. Be careful under your seats. Be careful under the pillow in the hotel, because it's a very dangerous spider. If you are bitten by the tarantula, you will have some problems. And people usually move around, dance, have a kind of frenetic activity, and it's a kind of hysteric behavior. That was a popular belief. If you see some of your colleagues during the conference doing something like this, playing the violin, this dance, which is called pizzica, in order to solve it. And somebody here close to Lecce, in a small town known as Melpignano, had a great idea to transform this popular belief in a big event, the so-called, a big concert, you know, the so-called Notte della Taranta, the night of Taranta. Just a few thousand people during the year. At the end of August, the last week, we have this Notte della Taranta, a big concert, okay? 200,000 people that gather there in Melpignano in the field, dancing, as you will do for sure during this conference, the so-called pizzica, this frenetic dance. In 1999, when the rector gave me this important task, I was a young researcher at this university. I was teaching general physics and also optics. And a young student came to me and said, I want to make a thesis with you as a supervisor, and I would like to study laser solid interactions, new laser devices. I said, okay, forget it. I don't have time to do that because I received an important task of this university. I have to install a new accelerator, a new center, unique in Italy. So I convinced this guy to change from new laser devices to AMS. I don't know if it was a good choice for him, because this guy graduated, then made the PhD in AMS. They became researcher, then associate professor. Now he is a full professor. It is also the vice director of the Department of Mathematics and Physics. I would like to introduce Professor Dr. QUARTA, Gianluca for friends, as you know. Please.
Yeah. Thank you very much. I also was 25 years younger at that time. And I remember, I didn't know what Lucio was going to say about me. So, but I remember when I was entering his office and I was asking for, indeed it's true, a thesis on the laser solid interaction, because he was part of a quite strong group at that time. And he was showing me a drawing of a lab, which was an empty room with the drawing of an accelerator. And I didn't know which was, the ion source and the beginning and the end of this machine. I said, it's just a drawing. Would you take a chance for this? And then I thought, and then I decided just to try. And yeah, it was a good choice, and I'm very, very happy of having done this choice 25 years ago. Now, before giving you a few general information about the conference, the organization of the conference, I would like to first invite Professoressa Maria Antonietta Aiello. She is the Deputy Rector of the University of Salento. Unfortunately, the Rector, Professor Fabio Pollice, is not in Italy, he is abroad for institutional duties. He is in Tajikistan, at the moment. So, Professoressa Aiello, she will make the greetings for our university. Thank you.
Thanks very much, Gianluca. Buongiorno a tutti e a tutte. Per me è veramente un grande piacere intervenire all'apertura di questo importante e prestigioso evento scientifico, la quarta conferenza internazionale sulle applicazioni del radiocarbonio all'ambiente.
Good morning, everyone. Thank you for being here. This is the 4th edition of the International Radiocarbon and the Environment Conference.
Un evento che riunisce, come ho avuto modo di rilevare dall'intenso programma, esperti che provengono da diverse parti del mondo in un settore sicuramente cruciale per poter affrontare le sfide ambientali del nostro tempo.
It's a meeting that unites and meets people from all over the world to face meetings and issues from this in these crucial times.
Ovviamente vorrei innanzitutto porgere a tutti voi un caro saluto, un cordiale benvenuto anche a nome del magnifico rettore che, come diceva Gianluca, per gli amici, è fuori sede, e anche a nome dell'intera comunità universitaria.
A very hard welcome even from the head of the university, who couldn't be present here because he was busy, and on behalf of the whole university.
Consentitemi innanzitutto di ringraziare gli organizzatori di questo importante evento, i colleghi del gruppo di fisica applicata del Dipartimento di Matematica e Fisica della nostra università e un particolare ringraziamento ai chairman di questa conferenza internazionale, i colleghi Lucio Calcagnile e Gianluca Quarta.
A very special thanks to the people who organized this meeting, people from the physics department and mathematics and physics of the University of Salento, and the chairman, Professor Lucio Calcagnile and Professor Gianluca Quarta.
Un saluto a tutti i componenti del comitato scientifico, a tutti gli autorevoli relatori. La partecipazione, come si diceva prima, di circa 150, se non sbaglio, relatori che provengono da più di 20 paesi europei, sicuramente farà dei lavori di questo.
Thanks to the professors and the people who organized, and all the professors and speakers who came from around 150 countries all over the world.
Sicuramente, dicevo, farà dei lavori di questo convegno un importante riferimento per la comunità scientifica internazionale.
Who will do a very important reference point for the international community.
È doveroso sottolineare da parte mia che questo convegno è soprattutto il frutto di un impegno costante e di un costante investimento, come abbiamo già avuto modo di apprezzare dalla relazione del professor Calcagnile, nella ricerca in questo settore. Un impegno che ha consentito alla nostra università di raggiungere livelli di eccellenza riconosciuti a livello internazionale. E mi riferisco nello specifico alle attività del CEDED che ha prima presentato il professor Calcagnile, il Centro di Fisica Applicata, Datazione e Diagnostica della nostra università, a cui consentite anche a me di dedicare qualche minuto.
I want to thank all the people who organized this meeting and everything they put in, all the study that's behind this organization, which is internationally recognized, and also thanks to the activity done by CEDAD.
Il CEDED, come diceva il professor Calcagnile, è stato realizzato a partire dal 1999 su incarico del rettore Angelo Rizzo. Ho vissuto anch'io quel momento storico e insieme da giovani ricercatori siamo stati mossi da tanto entusiasmo che per fortuna ci accompagna ancora oggi.
The CEDAD was founded in 1999 on behalf of Angelo Rizzo. It's a very historical power and with a lot of researchers, and we're all in it still.
Nel corso degli anni il CEDED ha rappresentato un punto di riferimento nazionale e non solo per la ricerca e il servizio di datazione e misura del radiocarbonio.
CEDAD has always been international reference point and in the research of radiocarbon.
Ha collaborato con numerose istituzioni ed enti di ricerca pubblici e private, svolgendo anche attività di servizio conto terzi.
Has contributed with institutions, either public and private.
Da un solo laboratorio, come abbiamo visto, quello dell'acceleratore Tandetron, nel corso degli anni il CEDED ha aggregato numerosi altri laboratori, nei quali si svolgono misure isotopiche applicate all'ambiente, ai beni culturali e a numerosi altri campi di ricerca tipici delle scienze dure, ma anche in ambito umanistico.
Not only there's the acceleration lab, but also a lot of other laboratories with that measures isotopic measures and others field of research and also human.
Vorrei inoltre sottolineare il ruolo fondamentale del CETED anche nella formazione dei nostri giovani.
I would also underline the fundamental role of the CETED in the formation of our young people,
I quali hanno la possibilità di usufruire delle facilities del centro e in particolare di quelle connesse appunto all'acceleratore Tandetron.
Who have the possibility to use the facilities of the center of the lab, in particular the one for the accelerator.
Una grande opportunità non solo per gli studenti dei nostri corsi di laurea, ma anche per quelli della nostra scuola superiore SUFI, della scuola di specializzazione in archeologia, della scuola di dottorato.
It's also a huge opportunity not only for our university students, but also for ISUFI high school students and archaeology and post-laureate.
Questo evento rappresenta senz'altro un importante riconoscimento internazionale alle attività di questo centro e un'ulteriore tappa nel percorso di crescita della nostra università.
This is also very important international recognition of our activity and also a huge stepstone of our university growth.
Infine mi preme sottolineare che per noi un grande onore ospitare come keynote speaker in apertura di questa conferenza il professor Walter Kuchera, fisico e docente dell'Università di Vienna.
It's also a huge honor to introduce the keynote speaker, Walter Kuchar.
Yes.
Sorry, who's a physics and professor at Vienna University.
Il professor Kuchera è uno dei padri della tecnica di datazione con il radiocarbonio, con acceleratori di particelle e delle applicazioni delle analisi isotopiche in diversi ambiti applicativi, dallo studio dei cambiamenti climatici alle scienze forensi.
Professor is a very It's very fun of the accelerator and the analysis application, isotopic application, and the study of climate change and forensic science.
Concludo questo mio breve intervento di salute rinnovando a tutti voi il più cordiale benvenuto, augurando a tutti voi un fruttuoso lavoro e una gradevole permanenza presso la nostra università e presso la nostra città. Grazie.
Thank you, everyone. I wish a good stay here and a very heartwarming welcome. Thank you.
Thank you very much, Professoressa Aiello. Now I would like to ask Loredana Tundo, Professor Loredana Tundo, representing the province of Lecce, which is this part of the southern part of Italy, and she will give us also some greetings from the president of the province of Lecce. Thank you very much.
Buongiorno a tutte e a tutti e con grande onore gli do il benvenuto a tutti i partecipanti a questo prestigioso convegno internazionale di fisica qui a Lecce.
Good morning, everyone. Thank you, everyone, for being here at this prestigious international conference here in Lecce.
A nome del Presidente della Provincia di Lecce, Stefano Minerva, che si scusa per non essere qui personalmente in quanto impegnato fuori su Bari.
I'm on behalf of the President of the Province, Stefano Minerva, who apologizes for not being here because some other business in Bari.
e dell'intera comunità provinciale, che desidero esprimere la nostra profonda gratitudine per aver scelto la nostra terra come sede di questo importante evento scientifico.
And also on behalf of our whole provincial community, we really want to thank because it has chosen our territory as a place for this important scientific event.
La fisica, con le sue continue scoperte e innovazioni, rappresenta un pilastro fondamentale per lo sviluppo della nostra società.
Physics, with its discoveries and innovation, is fundamental for the development of our society.
Siamo convinti che i lavori di questo convegno contribuiranno in modo significativo all'avanzamento della conoscenza in questo campo e apriranno nuove prospettive per il futuro.
We are sure that the works during this conference will contribute in a significant way to the progress of the knowledge in this field and will surely open new perspectives.
Lecce, con la sua ricca storia e il suo vibrante tessuto culturale, è da sempre un punto di riferimento per la ricerca e l'innovazione, in quanto caratterizzata da una grande varietà di ecosistemi, dalle coste marine alle aree interne.
Lecce, with its history and culture, has always been reference points for research and innovation because characterized by a huge variety of ecosystems from sea coasts and internal areas.
La nostra provincia è impegnata a sostenere e promuovere iniziative che favoriscono lo sviluppo scientifico e tecnologico nella convinzione che la conoscenza sia il motore del progresso.
Our province supports and promotes initiatives to develop scientific and technological development, being sure that knowledge is the real engine of the progress.
Il CEDAD di Lecce, affiliato all'Università del Salento, fiore all'occhiello della nostra provincia, rappresenta un punto di riferimento importante grazie a un team di ricercatori altamente qualificati e a strumentazioni all'avanguardia.
CEDAD, affiliate to University of Salento, the flagship of our province, is an important reference point. Thanks to a researchers team, more than qualified researchers team, and a high-tech equipment.
Desidero ringraziare gli illustri relatori che presenteranno le loro corpose comunicazioni scientifiche e il professore Lucio Calcagnile QUARTA per essersi profusi insieme a tutti coloro i quali hanno collaborato nella realizzazione di questo importante incontro scientifico.
Thanks to the prestigious lecturers and speakers who will introduce their scientific communications, and to the professors Lucio Calcagnile and Gianluca QUARTA for being part with everyone else of this important scientific meeting.
Auguro a tutti voi un proficuo lavoro e un piacevole soggiorno nella nostra splendida terra, di cui avete avuto modo di vedere le bellissime immagini che ha proiettato il professore Calcagnile. Grazie.
I wish all of you a good job, a good work, and a pleasant stay in this beautiful city. Thank you.
Thank you very much. Now I ask Dr. Giordano Anguilla. He is Deputy Mayor of the City of Lecce, representing the Mayor, Professor Adriana Polibortone, to give the greetings from the city. Thank you.
Grazie, buongiorno a tutti e benvenuti nella nostra splendida città. Benvenuti a Lecce.
Good morning, everyone, and welcome to our beautiful city.
Lecce non rappresenta solo il capoluogo della nostra provincia. Lecce rappresenta l'immagine di una regione nella regione, di un territorio specifico, di una tipicità italiana, ovvero il Salento, a cui è dedicato il nome del nostro Ateneo.
Lecce is the image of a specific territory, which is called Salento, which is the name of our university.
Salento è un concetto che il professor Calcagnile ha ben sintetizzato nella sua introduzione, quando abbiamo visto tarante, animali, una terra fatta di sole, di mare, anzi di mari. E veniamo quindi al tema del convegno.
Salento is a concept that Professor CALCAGNILE has already introduced before with Taranta, Sun, Sea. That's how we connect to the main theme of the conference.
Il racconto e la valorizzazione del nostro territorio non solo da un punto di vista scientifico, come il tema dell'acceleratore delle particelle potrà testimoniare, ma a tutto tondo. Non possiamo dimenticare infatti la difesa dei temi ambientali e quello dei beni culturali, che sono parte integrante di questo lavoro partito ormai nel 1999.
So we speak about the valorization of our territory, not only in a scientific way, talking about accelerators, but also about environment themes and historical beauties, who is a theme that started in 1989.
Lecce infatti non è solo la città del barocco, così è nota in tutto il mondo. Lecce è anche la città romana.
Lecce is not only the Baroque city that all the whole world knows, but it's also a Roman city.
Ed è, come dicevamo, una terra che divide due mari, lo Ionio e l'Adriatico, che poi in un punto chiamato Finibus Terre si baciano a Santa Maria di Leuca.
It is also a land between two seas, the Ionic and the Adriatic one, and we also have a place called Finibus Terre, where is the two seas combined.
Come amministrazione siamo impegnati da sempre nel sostegno degli studenti e nel sostegno all'università per progetti che mirino alla difesa e alla promozione del nostro territorio e alla crescita dei nostri ragazzi, al fine di consentirgli di lavorare e studiare qui e tenerli vicino a noi.
As a local administration, we support students from high school and university to defend and promote our territory, and their growth, because we want them to study and work here and live here in our territory.
È giusto e doveroso ricordare in ultimo che i dipartimenti di matematica e fisica sono intitolati ad Ennio De Giorgi, probabilmente uno dei più grandi matematici, fisici, scientifici della storia. È stato infatti verificato che molte delle scoperte successive a Ennio De Giorgi erano già state individuate dallo stesso.
We also have to mention that our Maths and Physics department is named after Ennio De Giorgi, one of the most famous mathematician and physician and physic. And a lot of discoveries following his death had already been discovered by him.
Sarà pertanto nostra premura e lavoro cercare di intitolare un luogo più adeguato alla memoria di questo grande uomo, una piazza possibilmente. Questo lo anticipo, è uno dei temi del nostro programma amministrativo.
We will also take care of naming something else after Ennio De Giorgi, such as a square, and this is an information I'm giving in advance as a local administration.
In ultimo, augurandovi buon lavoro, vi saluto ricordando forse un ultimo passaggio nell'introduzione, professore, ovvero un invito ai nostri ospiti ad assaggiare il nostro pasticciotto, che è tipicità oltre a quelle che aveva già illustrato lei in premessa, e augurandovi a tutti insomma buon lavoro porto ancora una volta i saluti del sindaco Adriana Poli e della nostra amministrazione.
Wishing you good work and a pleasant stay. I also wanted to invite you to taste our pasticciotto, which is another traditional typical food from here. And I am also speaking on behalf of the mayor, Adriana Poli Bortone. Thank you.
Bye.
Thank you very much. Now the last welcome address. It's going to be given by Professor Salvatore Rizzello. He is the director of our advanced ISUFI school and of the University of Salento. And so, thank you. Thank you, Salvatore.
Good morning. Thank you very much for inviting me in this prestigious conference. I'm honored to give you my welcome on behalf of the Higher Excellence School ISUFI of the University of Salento. The school is a center of higher education located in a college within the Ecotechnic campus, very near to the seat of the Department of Mathematics and Physics. Its aim is to enhance the quality of the university's teaching offer and to foster the development of scientific knowledge, the recognition of merit and the development of higher education activities with interdisciplinary, international and collegial futures. Founded in 1999, it was institutionalized in 2005 by the Ministry of Education, Universities and Research. It's part of the national system of university higher schools and is the only higher school in peninsular Italy to be located south of Rome. The school selects young Italian and foreign talents exclusively on the basis of merit and offers them an education of excellence to supplement and complement ordinary university courses. The significant costs of this training, characterized by residency and internationality, are borne entirely by the Italian state. Students admitted to the school must enroll in a department of the University of Salento and follow the course of study envisaged for the bachelor's degree and the master's degree in all faculties. At the same time, they must participate in the specific advantage training activities organized for them by the school, including 2 language lectures, colloquia, seminars, and lecture series of a disciplinary and interdisciplinary nature. In total, 250 hours per year. They must also undertake at least 1 semester of study abroad. Moreover, students are involved in a lot of activities to acquire soft skills, including music, theater, arts, and debating. They are also fully involved in high-level international activities, as the recent prestigious Summer Excellence School on Interdisciplinarity and the 32 Congress NCAT on Culture That Matters, Interdisciplinary Approaches for Sustainable Future. At the end of the training courses, the Ministry of Universities and Research releases the equivalence of the license qualification awarded to students who complete the 5-year courses to a second-level university master's degree. I hope you have soon the opportunity to visit the school and our college. In the meantime, allow me to extend a special welcome to the students admitted to participate in this prestigious conference. For them, I'm sure this is an important opportunity for growth and a great opportunity to take part in a conference that sees the participation of very qualified scholars from all over the world on issues related to environmental monitoring, cultural heritage, and climate change. I would like to reserve a special thanks and my warmest congratulations to Professor Lucio Calcagnile and Professor Gianluca Quarta, and all people contributed in organizing this very extraordinary program of first-rate conference. I'm not surprised about it, because Lucio and Gianluca, together, all components of their teams are involved from decades in producing high-level research activities and publications. I remember when we visited the CIDAD laboratories, my surprise in knowing the magic of the radiocarbon and the pride of having such laboratories in our university. Thank you, Lucio and Gianluca, also for this. And I'm pleased in stressing that you are both members, respectively, of the Scientific Committee and Teaching Board of Higher Excellence School, ISUFI, of the University of Salento. To conclude, I'm glad in addressing to all speakers and participants my warmest welcome, a fruitful conference, and a pleased stay in Lecce. Thank you very much.
Okay, thank you very much. And now I will give you some practical information about the conference and some general information. First of all, before I forget, as Deputy Director of the Department of Mathematics and Physics, I bring you the greetings and the welcome on behalf of the Director, Professor Campiti, who unfortunately cannot be here for other institutional duties. And we are very honored and proud as department to host and also to have supported the organization of this conference. Okay, now some practicalities. First of all, you see that we do not have parallel session as it is the use on this series of conference. You see that we selected 6 different topics, which goes from methods, so both machines and sample preparation, atmosphere and terrestrial environment, anthropogenic effect, past environment and climate, marine and tropical environments. And I also would like really to warmly thank the member of the International Advisory Board and also the session conveners for the help they gave us in the selection of the abstract, in setting up all the sessions, and also for those of them who will chair the session for the help they are giving or will give in the organization of this conference. Then we will have 2 poster sessions. The first one is tomorrow in the afternoon, and the second one on Thursday in the room which is just behind the wall of this room. And another information, for those of you who sent the files to be printed, they can be collected at the registration desk. They should be already there. In case, just let us know. Now some numbers. We had so far 150 registered participants from 20 different countries with 63 orals and 71 posters. And you see that this is a general overview of the conference. It's going to be a quite busy week, and we have a quite tight schedule. So I really please you to be on time during your talks, and also I invite the chairperson to try to respect the timetable, but of course be on time. But we are in Italy, so try to be on time, and we are in southern Italy, so more or less. But we would like not to spend the nights in the castle, so try to do your best. We will have 2 special lectures. The first one is going to be this morning by Professor Kucher. I will a little bit overview the application and the basics of the isotope language, and I just took this picture of Walter this morning, and and then tomorrow we will have the talk by Professor Paul Arthur. He's Professor of Medieval Archaeology at the University of Salento. He will talk a little bit about the history of this wonderful building, and also about the history of the city of Lecce during the Middle Ages. Now, there are some special events. The meeting point for these events is going to be the main gate of the castle. So we will meet always there. The first one is tomorrow. We have the Lecce guided city tour. Of course, you have all the information in the program. And on Wednesday, we will move to Gallipoli, but I will give you more information about this. And on Thursday, there will be the CEDAD laboratory visit and the conference dinner. So do not forget, the meeting point is at the entrance of the castle. Now, on Wednesday, all the sessions will be held at the Hotel Costa Brada in Gallipoli. Gallipoli is a town in about 40 kilometers southeast from Lecce. And in the afternoon, we will have a free old city tour. And also my suggestion is do not miss the sunset. You have different bars and pubs where you can enjoy the sun setting down. On Thursday, we will have the laboratory visit, which departs from here at 5:30. Soon after the end of the second poster session, we will go to Brindisi by bus, visit the lab, and soon after we will have the conference dinner in Castello Monaci, another castle. And you see here some of the pictures. So it's important, we are not going to come back in Lecce after the laboratory visit. We directly go from the lab to the conference dinner. So Wi-Fi connection, there are all these QR codes around. You just scan it and you can connect to the free Wi-Fi. You see here the login details for logging into the Wi-Fi connection. Also, we decided not to print the abstract booklet to save also paper and trees. And you have a QR code on your badge. You can scan it with your devices and you can download either the program and also all the abstracts of the conference. And I also would like to thank the Direzione Nazionale Musei and the director, Dr. Pietro Copani, for having given us the possibility to be in this wonderful building. And also, please consider that we are in a building which is classified as a cultural heritage by the Ministry of Culture. So you see around there are stands and exhibition of real archaeological objects, so please try to be careful. And there are also areas where food and drink is not allowed, for instance in the poster area. So you are not allowed to bring food and drinks with you. And also, again, we already had greetings this morning. I would like really to thank the institutional supporter, Regione Puglia, Provincia di Lecce, Città di Lecce, and Scuola Superiori Sufi, but also the sponsor, PPQ Sense, Ion Plus, Thermo Fisher, Barnas Mass Spectrometry, A2A, Maidos, and Martinucci for the support, also the financial support they gave for the organization of the conference. So, thank you again. And again, as I said, it's a tight schedule. We have a lot of talks, a lot of posters, but try not to be disturbed by the visit of the city of Lecce. So enjoy the city, enjoy our nightlife, and I really wish you a fruitful and successful conference. Thank you very much.
So now, in honor of all the attendees of this conference, we prepared just a short musical moment. What? I don't understand. So in Italy we say, questo è il bello della diretta. This is what happened when you have a live broadcast. We don't have the pianist? What did you say? So what can we, in 1999, I wrote a music with my young collaborator, since we really don't have the pianist. Yeah. So I will try to just to perform this music. I hope it will become very popular. The title is We Are the Shaded. Are you sure?
ragazzini ma fai un uccello, la macchia mallugori, la macchia mallugori, la macchia mallugori, piano piano. Ah ah ah, diavolo parla a tuppicare, con la spina tra l'upede, con un forza camminare. Ah ah ah, diavolo parla a tuppicare, con la spina tra l'upede, con un forza camminare. Sulle sospiri tua m'hanno chiamato. Abueli, mo lo vedo di venire, mo lo vedo di inchinarmi dalla mano si va. Abueli, mo lo vedo di venire, mo lo vedo di inchinarmi dalla mano si va. E te lo ritornati, ti lo ritornati per nada piada. La compagnia va, sa subito va, la compagnia va, no la chiamata. Abueli, ueli, quella, nada moda starti buona, tu di me non ti scuda. Abueli, ueli, quella, nada moda starti buona, tu di me non ti scuda. Abueli, ueli, quella, nada moda starti buona, tu di me non ti scuda. Abueli, ueli, quella, nada moda starti buona, tu di me non ti scuda. Abueli, ueli, quella, nada moda starti buona, tu di me non ti scuda. Abueli, ueli, quella, nada moda starti buona, tu di me non ti scuda. Grazie.
Elodie.
Grazie mille ragazzi, grazie. Wow. Sono felicissima.
Okay, I have to say a few words. Lucio, this is conspiracy of Lucio. Well, I can only say two things. Our world is in big trouble, and Niels Bohr once said, some things are so serious you can only make jokes about it. The other thing I wanted to say is I come from Vienna, and we just heard such a phenomenal concert of a young, almost Mozart-like person. I'm reminded of Beethoven, who once said to his students, making a mistake means nothing, but playing without passion is unforgivable. So in this sense, I will try something I played some time ago. In Vienna, we had, of course, many visitors from many countries over the times, and one group which I remember in a way, they're still coming occasionally, are the gypsies from Hungary. So I'm playing a small melody of gypsies, and I'm still thinking of my boss at Argonne National Lab, John Schiffer, who actually was from Hungary and spent all his life in America, but originated from Hungary, and at the end of his life, he unfortunately died 2 years ago. We had a lot of discussion about the time right at the war and after the war. Thank you.
So it's better that we have the coffee break now, okay? From the other room, and you can go.
Good morning. How was the coffee? Was okay. The panzerotto was okay. The croissant. Please have a seat. Okay. Thank you very much for coming back after the coffee and being almost in time because we are in the south of Italy, as you heard, and I think we don't have to spend too many words anymore to say how beautiful is Italy, how nice is Italy from the culture point of view, but also from the science point of view and music. So we have a full week to enjoy this. And as Italian originally, I can only say that, you know, I'm from the north, so, but it's beautiful. Italy is beautiful. And after so many words about Walter and his performance, to introduce this, his keynote, I would like to remind something that maybe not everybody knows about Walter. He just gave me his reference this morning that he's probably the only one that was present at every AMS conference, from the first one, and he's going also to Guilin now, so he's keeping going, and he's becoming, you know, a kind of column in this community of C14, AMS, and so on. And I'm very happy to invite you to give us your keynote. In this world where artificial intelligence is taking over our talking, you know, we never know on the telephone if now is a person or not. Having your keynote about reading and interpreting the isotope language. I hope that the artificial intelligence is not yet ready to fake Walter.
I'm in a way speechless after this performance on the piano. I've never heard in a long life such a talent at that age. I attended recently a competition of young people in Salzburg, and all of the people of the age of this player and younger were from Asian countries. So to see somebody from one of the countries where music originated in a way with such a young age and such a talent was just mind-boggling to me. Okay, I have to give a talk which I suggested as one of several topics to Lucio and Gianluca, but somehow they chose this very general talk. Of course, I know this is impossible to describe this whole field in all its different facets. So I will try to do the following. First, I will talk about some of the pioneers which I admire in the field of isotope research. Then after that, I will jump to very recent times, the last few years, and I was amazed on a few topics which caught my mind at least, and I will give you a few examples. This is, of course, a very subjective selection of topics, but within the time given, it's not possible to cover the whole field. So let's start. The person who initiated this word of isotope language was actually Hans Oeschger. He told me a couple of years ago, when he was still alive, perhaps someday we will understand the climate through the isotope language. Of course, this is a very great statement, and we all know in this room that isotopes are being used on in various fields as a means to understand more about our climate. Now, in fact, I played music with Hans Oeschger many, many years ago at AMS 4 in Niagara-on-the-Lake. And this was in 1987. So if I did do the calculation right, it's 37 years ago. I played a Vivaldi concerto together with Hans Oeschger, and the guy on the piano is John Ruckledge. Some of you may know him from Toronto. Now I will just switch to a few pioneers of stable isotope language. And of course, again, this is a choice I just took. Who was perhaps one of the important people at the very beginning was Harold Urey. Harold Urey discovered the deuterium in 1932. This was the year when Chadwick discovered the neutron, in the same year. So Urey didn't know anything about neutrons. He just did actually not mass spectrometry, but optical spectrometry. In a discharge of hydrogen and also enriched hydrogen, he was looking for a faint little signal in his spectra of the Balmer series. Yeah? And he also, later he tried to estimate the relative abundance of deuterium in hydrogen. And I think he got it a little too low, the number, because at that time the first mass spectroscopists also started to look for it, and they found a number which was a factor of almost 10 different from what Urey was originally arguing. But on the other hand, he was clearly the discovery of the deuterium as the first person, and that earned him the Nobel Prize in 1934. Now, for those who are in mass spectrometry, one of the real pioneers, he's sometimes called the father of mass spectroscopy, is Alfred Neer from the University of Minnesota. And I mentioned one particular discovery. At the time, it was known potassium is radioactive. But what is the radioactivity of potassium? It's not the main isotopes, which are stable, 39 and 41. So he did the mass spectrometry, and he found this 10 to minus 4 abundance little peak in his mass spectrum. Everybody thought, well, this is probably calcium-40. But he was very clever. He actually had an ion source where he changed the impinging energy of the electrons. The ionization potential for potassium is different than for calcium. And in this way, he could confirm that this little peak, which he saw between the huge peaks of the stable isotopes, that it is potassium-40. Now, the interesting story of potassium-40 is as follows. When Carl Friedrich von Weizsäcker, who was experienced in astrophysics already at the time, in the mid-30s, when he heard that potassium-40 is radioactive, he thought, well, we know the radioactivity of potassium-40 is the beta decay to calcium-40, but perhaps there is a different decay to the other side, to argon-40, and perhaps the overabundance of argon-40 in the atmosphere is due to this decay of potassium-40. And he even made an estimate of the half-life. He estimated if all the argon-40 in the atmosphere comes from potassium in the Earth's crust, giving off argon-40 over billions of years, then the half-life must be in the order of a billion years. So his estimate of the half-life was even correct. It's a fantastic little paper. I only know the German, it's in a German journal, but it showed already at that time that somebody who is able to connect different fields can find out something which you never think of. So it is actually the dual beta decay what he discovered, Weizsäcker, when he heard this result from Otto Neer. Now, the next person, of course, should be well known in Italy. Cesare Emiliani did his undergraduate and first graduate work in Bologna, and then he moved to America, to the University of Chicago, and did his PhD together with Harold Urey. And Cesare Emiliani stayed all his life in America, later moved from Chicago to Miami, and he developed the Delta 018 method analyzing foraminifera in deep sea cores. And this was the first hint which he found that there is some cyclic timing of possibly ice ages following the famous theory of Milankovitch, who you know, I mean, most of you know that, of course, the Milankovitch theory, which says that the ice ages are triggered by the changing of the orbital parameters of the Earth around the Sun. There are three different contributions to it. I can't go into detail of that. But this was the first hint. Interesting enough is that when the ice core measurement started, Cesare Emiliani, he always thought the signature he can read on oxygen 18 has to do with temperature. And it turned out that's not the main effect you see even in the deep sea sediments. It has to do with the fact that if there are glacial times, isotopically lighter water is being transported to the land and deposited there. The ocean goes down by 100 meters or so and gets heavier, isotopically heavier. This is something he was not considering as a good explanation at the time. This is what other people said who worked in this field. In addition, he was convinced that the cycle is 40,000 years and not 100,000 years of the ice ages. Both of these assumptions, in a way, were wrong, but he was still the pioneer to develop the method as such. Okay, the next person is perhaps not so well known to many people of you, but Fritz Houtemanns was actually the predecessor of Hans Oeschger in Bern. And he had a very, very checkered life, really. But what was interesting is that he started essentially isotope geochemistry in Bern, and Oeschger was his follower. And so he did the first correct estimate of the age of the Earth at the time by using material from meteorites, which showed the original uranium to lead ratio. If you take this fine material on the Earth and try to find the original lead to uranium concentration, you would not find the right, because there's always some decay already happening from uranium into lead. Anyway, this was Fritz Houtemanns, and the last one on this figure is probably known well to you, Willy Danskart from Copenhagen. He really was the father of ice core research, and all his life he worked on ice core climate research, and he figured that delta 018 and delta deuterium is so useful to follow the different ways the climate is printing its history in the ice cores. Okay, I have another picture here which shows Fritz Houtemanns at his later age discussing with Harold Urey in Bern. Harold Urey was considered to really be the great first person to understand all the effects of stable isotopes. Now let's switch quickly to some pioneers of radiocarbon in the decay counting era. Of course, Willard Libby has to show up, who invented carbon-14 dating, again at the University of Chicago in 1947. He rightfully received the Nobel Prize in Chemistry in 1960. There was another person close to him. Jim Arnold was actually his student. And Jim Arnold, his paper shows the first radiocarbon measurements on samples of known ages. And this famous paper showed the first time that radiocarbon dating may actually work. Yeah? This was not known for sure at the time. Next is Hans Süss. Hans Süss was actually a nuclear physicist, was involved in the shell model development early on, and later he switched to radiocarbon and was interested in the effect of fossil fuel on the carbon-14 content in the atmosphere. In 1955, it's now generally called the Süss effect, and as we may hear later in this conference, of course, the fossil fuel effect continues. It continues all the time. In fact, CO2 is continuing in the atmosphere, and also this effect on the carbon-14 because we add dead carbon to the CO2 from fossil fuel. Okay, the last person on this list is Hessel de Vries from the University of Groningen. Hessel de Vries was, in a way, almost like a meteor who burned out very, very early. He had a tragic life. In fact, he killed himself because of a love story. This happens even in Holland, not only in Italy. He killed it. Anyway, but Hessel de Vries was the first one who observed that carbon-14 is not smooth over the years, and sometimes it's called de Vries wiggles, this effect. So he was the originator of the effect, the fact that carbon-14 is not constant over all times. And that, of course, gives us big trouble in the calibration. Okay, so these are the original people with radiocarbon, and I'm now switching to some radiocarbon pioneers in the atom counting era, the EMS era. And again, some of you know the people very well. One is Rich Muller from Berkeley, who did the first measurements on a cyclotron with carbon-14. Very difficult because he used positive ions and he had to get rid of nitrogen, and this was a tour de force. Rich Muller, by the way, was a student of Louis Alvarez. And Louis Alvarez initiated using the cyclotron as a mass spectrometer originally because he asked Richard to help him. Louis Alvarez was an old man at the time, but Rich Muller should help him to look for quarks, for free quarks, using the cyclotron, tuning it to masses which do not exist regularly. But then he actually found that you could use it for carbon-14 dating. Now, the other people you also know very well, Harry Gove, who actually organized the first AMS conference in Rochester in 1978, where I had the good luck to be present there. And there were several other people in the same year of 1977. All of these people in 1977 published papers. Ted Litherland from Toronto, and also Ken Purser, who later became so important in producing AMS facilities. They together used the tandem accelerator in Rochester to measure carbon-14, and then there was Earl Nelson at McMaster University in Hamilton, and these people really established the AMS technique in 1977. Okay, now if we look at the summary of elements and isotopes, just in general, I have this information from the nuclear chart, which just came out in 2022. Well, we all know they are stable and radioactive elements, and the total number of elements is 118. If you look at isotopes, well, it's clear that there are many more radioactive isotopes than stable isotopes. Total of about 3,300, and they're still continuing to get more of them. The extremes are also somewhat interesting. The largest number of stable isotopes per element has 10 stable isotopes, and the largest total number of isotopes per element is actually mercury, which is 47 isotopes. The smallest number of isotopes per element is oganesson. Of course, this is the heaviest element we know, and only one isotope so far has been observed. And there's a big effort now going on, again also in Berkeley, not only at GSI and Dubna and also Riken in Japan, but also in Berkeley they rejuvenated their program to look for element beyond 118. It mainly has to do to get targets available, very heavy radioactive targets which you could bombard to reach out into this region beyond element 118. Okay, now I'm switching to some recent highlights which I find interesting, but again, this is a very personal sort of choice. Let's start with something I consider in a way a quantum leap in radiocarbon dating, the famous Miyake events. Unfortunately, Fusa Miyake is not here, but I'm sure she will show up at the AMS 16 conference in China. This is absolutely amazing. If you worked in radiocarbon for many years and you know how many troubles you have in calibrating and finding sometimes regions which are impossible to be used for precise carbon dating, these Miyake events were really something very exciting. This is a picture of Fusa Miyake, and this is the famous picture which she showed in 2012, already 12 years ago, that there is an excursion in Japanese cedars if you analyze them year by year. And this excursion happened in just 1 year. And this is an absolutely fantastic signal. If you can measure it in 3 rings, of which you know the absolute age, you have a fixed point in time for carbon-14. If you find this signal in other material around the world, if it actually shows up around the world, then this is something, oops, sorry, this was too far. Okay, so this significant 1-year excursion of carbon-14 were measured in 3 rings of Japanese cedar, and there was a second one in 993 AD after the first one. Both were published by Miyake in Nature Communication. Then, in the ensuing years, these events were confirmed in 3 rings from 5 continents. So it was a global event, not a local event. This was very important. And then, from then on, a number of other observations were made, and also some interesting applications. The one very interesting, I found at least very interesting, was the evidence for Europeans in the Americas. On the left side, you see a global map, and it is suspected, was suspected, that the Vikings, or some people related to the Vikings, were the first one to reach actually Northern America, Newfoundland. And this lady on the bottom, she actually did excavation in the 60s at a site which showed to be man-made. And later, many years later, in Groningen, they measured material from this site, and they found very clearly in these 3 rings which they measured from this time, they found the signal of the 993 AD event, this strong increase, and going out of these trees to the felling date or waning edge, they could actually determine the time when this material was used back in 1021. So they argue that now they know within 1 year when the first Europeans arrived in America. Interesting story. So the next one just came out recently, is an absolute dating of a Neolithic site in northern Greece. This has to do with an excursion which was observed previously in the year 5200 BC, so quite some old time. To this day, by the way, one does not know for sure what the cause of these excursions are. The general assumption is it's energetic particle outbreaks of the sun, so sometimes called solar storms, and but it's not absolutely sure, and especially one doesn't know where they come. They're completely random. There's no theory which says the sun has to erupt at a certain time to make these high energetic particles. Okay, so this site in northern Greece. To the left, you see which part of Greece is being investigated. There's some lakes, and there's an old site with a lot of trees. And within these trees, they very clearly saw the signal from 5,200 years BC. This one-year excursion and having several trees with tree rings and measuring year by year, they could very well establish, fix the date of this particular archaeological site. The last example is actually, I'm not sure all of you have seen this paper. It's not so easy to see these papers. This is by the French group around Edouard Bard that they found a carbon-14 spike in the late glacial period in southern France. This is in absolute time, this is 14,000 years ago. Okay, thank you. Sorry. Oh yeah, this is Edouard Bard. Yeah, Edouard Bard led this particular investigation where they actually collected a number of trees which apparently are preserved in sediments, river sediments for a long time. And they found this spike here at 14,300 years before present. This is the oldest spike, to my knowledge, which has been found, and this allows now, again, to use it for other applications. I don't know which one. Okay, I want to mention an archaeological highlight, to me at least. This is by pure accident. I didn't know that Elisabetta would be the chairperson here, because that's something I admire in the sense, is it really possible to establish accurate dates, absolute chronology of the kingdom of Judah? This is during the Iron Age, and all people here know that the Iron Age has this plateau, and it's very difficult to do any precise measurements. But this group around Elisabetta, they did a tremendous job in actually digging into old remains in Jerusalem. How to get access to this is another story. In any case, you see the calibration curve and this complicated structure. And by using very, very detailed studies of the material which they found, the term of microarchaeology is being used by her group. And this seems to be possible to actually establish an absolute timing for this period. I cannot talk about anything in this field, but Elisabetta is here. You can ask her if you have questions. And they published this paper just recently. Now, the carbon-14 bomb peak, of course, is something very familiar to everybody here. And there are many, many applications. I once gave a talk and called it the ugly and the beautiful. And you know that, of course, that the carbon-14 peak was produced by the atmospheric nuclear weapons testing. The one thing I always like to point out is, because it's rarely shown, when you actually generate carbon-14 as a new atom by the reaction of neutrons with nitrogen producing carbon-14, either through cosmic ray neutrons or neutrons from the atomic explosions, it goes through a two-step process before it turns up to become CO2. This I learned from Paul Crutzen. He told me that it's not a direct oxidation of carbon-14 to O2, but it actually goes through an intermediate step, first producing carbon-14 oxide, monoxide, and then in a second step with the OH radical, the CO2. So it is a sensitive measure. The carbon monoxide actually is a sensitive measure of the OH radical concentration in atmosphere. We had a program on this. But in any case, I just want to point out, don't believe these figures which always show carbon-14 generated and then CO2. It's not directly produced. There's a two-step process. Okay. Now, the one outstanding thing I feel in the use of the carbon-14 bomb peak, and we hear probably more about this later in this conference, especially in connection with forensic studies, the one outstanding thing I found was determining the age of cells in humans. I actually saw this in a note in the newspapers in Vienna. And when I saw it, I immediately called the lab in Stockholm. And in this special department of cell and molecular biology at the Karolinska Institute, famous institute, you know that they always determine who gets the Nobel Prize in medicine. They had this fantastic idea, which is given in the first paper. Please read this with me. Most molecules in a cell are in constant flux, with a unique exception of the genomic DNA, which is not exchanged after a cell has gone through its last division. The level of carbon-14 integrated in genomic DNA should thus reflect the level in the atmosphere at any given point, and we hypothesized that the determination of carbon-14 levels in genomic DNA could be used to retrospectively establish the birth date of cells in the human body. Yeah? This is a fantastic theory of biologists, yeah, that this could actually work. Yeah. And here you see what can work. There's the bomb peak, of course, the carbon-14 excess through the bomb. And you see a person with a lifespan of something like 60 years. And if you measure, extract cells after the person died and determine the carbon-14 content in it, you find that different parts of the body point to different times of his life or her life. And so this is a fantastic method to actually find out when cells are being born. We did one collaboration with this group some time ago where we investigated the olfactory bulb in the brain, the smell center, yeah? It turned out all the people we investigated were 5 individuals. They were born before the bomb peak, and none of them, 60, 70 years later, showed any increase of carbon-14 in the cells of the olfactory bulb. That is, no new cells were produced after birth for the olfactory bulb only. But then they had this one fantastic paper where they showed that in one of the most important parts in our brain is the hippocampus, where memory is being stored and many other things. And what is shown here on this, more than 50 individuals were investigated, and these experts in biology, they can actually separate neuronal cells from non-neural cells of the brain. And what is shown here is that every point is the birth date of the person, yeah? And if the signal is above for people who were born before the bomb peak, is above the birth date, that means that some cells were formed later in life. On the other side of the peak, you see that it indicates if the signal is below, that it points to a later time in their life. And so they clearly showed that there is some new cells, neuronal cells and non-neural cells are being made in adult. This is very important, of course, for any brain damage. Okay. Now a question, I'm supposed to talk about the climate, but a question relevant to climate change is this question. Was Greenland nearly ice-free at any time during the last 2.5 million years? And there are people who investigate this. And the two papers which came out also not long ago, one actually very recent, one is Jörg Schäfer from the Lamont Doherty Earth Observatory, and the other one is Paul Bierman from University of Vermont. In short, what what Schäfer did, they investigated material on the bottom of ice cores, the rocks on the bottom of the ice cores, and they measured beryllium-10 and also chlorine-36, both, aluminum-26, sorry, beryllium-10 and aluminum-26, and it was clear that only this material, the bottom rock can contain this if there was no ice. So the cosmic rays can actually produce these isotopes. And if you find out actually the ratio of aluminum-26 to beryllium-10 allows you actually to do some dating in a way, because they have two different half-lives. Beryllium-10 half-life is about a factor of 2 longer than aluminum-26, and so the ratio changes as time goes on. And it's at the beginning, this ratio is known pretty well. It's something like 6 to 7, and then as a function of time, with a effective half-life of 1.5 million years, it's getting smaller and smaller. So from that, Jörg Schäfer and his group concluded that Greenland was nearly ice-free. Now this guy, Paul Biermann, actually first argued against this because they investigated sediments, and sediments off the coast of Greenland, and they didn't find any evidence that there was no glacier covering Greenland for a long time. But in a recent paper, they actually changed in a way. They confirmed the ice-free thing by finding plant, insect, and fungi fossils in the bottom rock material, of ice cores in the center of Greenland. And so there is quite likely that at some point Greenland was ice-free or partly ice-free. And as you all know, if all the ice of Greenland melts, the sea level will rise by 7 meters. By the way, if all the Antarctic ice will go away, it will be another 70 meters. So at that time, we will be drowned. Maybe even this in Lecce, you will be drowned. Okay, so this is now an event which actually did change the climate, for sure. You all know that. the famous meteorite or asteroid, whatever you will want to call it, which killed the dinosaur, people estimated that it must have the size of Mount Everest, the meteorite which came down to the Earth. And that did indeed some damage to the climate. In fact, it is well known or accepted that the dinosaur died out in 66 million years ago. Why do I show this thing? Because very recently, they did an intensive mass spectrometric study, not with AMS, but with ICP-MS, with high-resolution ICP-MS, for ruthenium isotopes in this layer, which supposedly was produced by the impact worldwide. And if you look at the figure to the left, please notice at the bottom, if you can see it, this is not delta notation, but epsilon. Epsilon is a factor of 10 smaller than delta. It's 10 to minus 4 in units, epsilon. And they measure fractions of epsilon. So the precision must be tremendous to actually establish numbers on this figure. And what you see is that the green and the red line are meteoritic types, which are different from the material which they apparently collected from this impact of the dinosaur-killing asteroid. And so they are quite sure that it does not belong to this other type of meteorites, but belongs to a so-called carbonaceous chondrite, probably originating from the outer solar system. Okay. Now, a very recent event. This is the last special thing I show. A very recent event was actually a meteoritic fall, which happened beginning of this year in Germany. Not far from Berlin. It just missed Berlin by 50 kilometers to the west. Now we had a talk given in Vienna by one of the people involved in that, and he told us about this worldwide observation system. Yeah? The sky is being studied, being looked at all the time to find possibly something which actually comes down to the Earth. Most of the small meteorites, never reach the Earth, but this one was big enough, so they actually came down in this special place. So this is the field which where all these breakup products of the meteorite were collected, and you see the samples were from a few grams to down to 1 gram material. And this paper was published just recently in Meteoritic and Planetary Sciences. So Tim Joule should know that, of course, very well, and the discussions about it. Why I'm showing this is because, for me, this is an experiment which used the whole machinery of isotope methods. It's just amazing if you look at this list. It used almost any method you can imagine, yeah? Electron microscopy, electron microprobe analysis, inductively coupled plasma, atomic emission spectrometry, inductively coupled plasma sector field mass spectrometry, gas source mass spectrometry for oxygen isotopes, multi-collector inductively coupled plasma mass spectrometry for titanium isotopes, then noble gas mass spectrometry for helium and xenon, and gamma spectrometry in an underground lab near Dresden. Also AMS measurements. In fact, these 2 measurements were performed in Werra for aluminum-26 and calcium-41. Magnetic stability measurements and Fourier transform infrared spectroscopy, where you can identify materials. So it was an absolutely astounding collection of measurements being performed on this very unique fall, which was actually being observed. A small thing, why it has this very strange title, yeah? Cosmic Piers from the Havilland. Riebeck. There's actually a connection. This, of course, is only well known in Germany. There was a famous poet who made a poet about exactly this area, a very rich person who lived in this area, and he gave, his custom was that he gave to the children pears every year when the pears were ripe, yeah? He gave it off. And when he died, his son was, he expected his son would not continue this trade. So he asked that a pear were put in his grave on his sarcophagus, and out of this grew a new tree and produced the pears which the children could still take. So this is the connection to this title, Cosmic Piers. In this case, it was a meteorite, not the pier which came down just at this point. Okay, I think I'm at the end, more or less. I want to close with a statement of 2 great Earth scientists, I would call them. The one we talked about already, Cesare Emiliani. Please show hands if you have ever seen this book which he has written, Planet Earth. Anybody knows that? Nobody. This is an absolutely amazing book. I came across it just recently. He wrote it at the end of his life in 1992. It has 700 pages and describes the whole Earth in a detail you wouldn't believe. It starts from Big Bang and ends up with the creation of life. And it is just amazing, his knowledge about the whole world, which he's written down in this book. And he says it is written for, not for laymen, but there's not much mathematics in it. It's written in a beautiful way. And I just show this few sentences in the preface. He said, our planet is at risk. The current explosion in the human population is forcing us to a simple but pivotal choice: stabilize the planet or perish. The first few decades of the next century will bring grave crisis. And while this was 30 years ago, this book was written. Environmental, economic, human. Only if we achieve a close understanding of the system of which we are part, how it came about and how it works, we will, the next generation, be positioned to cope with the emerging problems. Okay, and the last person whom I met personally is Paul Crutzen. Paul Crutzen actually wrote a paper which was published in the year of his death, and it turned out to be a paper which was published. You see the reference. He got the prize in Russia, at the time, and the paper is called "We Live in the Anthropocene, So Will Our Grandchildren." And there he makes the following statement at the end: our curiosity and eagerness to understand everything surrounding us, including ourselves, makes science overturn each and every stone. At the same time, it is difficult to escape the impression that at the present stage of the Anthropocene, which we unfortunately cannot refer to as the early Anthropocene, not knowing how long it will last, humanity as a geological force seems to be somewhat unbridled and helpless. To children and young people, 87 years, he was 87 at the time, seem an eternity. At the age of 87, one sees this differently. Nonetheless, let us hope that through the acceptance and awareness of our epoch, the Anthropocene, 20 years after the first little publication about it in a newsletter, the actions needed to limit major irreversible damage to our planet, especially the many serious effects of global warming, will now gain the required momentum. Let's hope that he is right. Okay, that's the end. I have nothing more to say. Thank you very much.
Thank you, Walter, for this enlightening opening talk. Any question for Walter?
It's time for lunch.
Walter, I have a question for you.
Yeah, okay.
You mentioned so many people and you explained to us a lot of their science and their input. What is your vision for the future? Can we put your picture there and quote you?
I think, well, what can I say? I can actually only quote my wife, who always quotes Einstein. And Einstein said, you can either consider the universe as friendly or as hostile. So if we accept that the universe is friendly to us, then that's the only hope we have. So we will continue to live. And every time, especially now, of course, at my age, I'm fortunate to actually have already a great-granddaughter and see the new life is the only answer we have. Everything else is going away. People are still killing each other to the thousands. But new life, you cannot do anything. It will persist. And when we saw this young boy playing this beautiful music, I mean, this is another indication that life is going on. Yeah. That's the only answer I have. Sorry.
So for this conference, we decided to have three prizes. So the first one was given by the rector. The rector is not here, but probably will come during the week because he's abroad. And the winner is, for this prize, Walter Kuchera. Please stand up. By the rector of this university. You can open, Gianluca. This is the seal of the University of Salento to Walter Kuchera, professor of the University of Vienna, founder of the Vera Laboratory for the fundamental contributions in isotope physics and accelerator mass spectrometry. Professor Fabio Pollice, rector of this university. Congratulations.
Yeah, then we also decided to award 2 prizes, which will be decided across the conference. One is for the best oral communication and another one for the best poster. And Tim Jewell will chair the committee for the selection of the 2 presentations. They are intended mainly for early career scientists. And of course, the committee will be the International Advisory Board. And on Friday, the closing ceremony, we will announce the winners.
It's for early career scientists. I don't know what early means, probably much less than the radiocarbon half-time, for sure. And there is an additional award. I just decided this night for this. You see on the back of your badge, there are a few sentences, Italians and also a dialect. Usually when you do the presentation, you finish saying, okay, thank you for your attention, and so on. There is an innovation in this conference. If you want to participate to this award, you have 2 possibilities. Instead of saying thank you for your attention, the first possibility that you have is this one. It's on the back. You cannot miss. Okay? You have to see. Everything is recorded in this conference. You see, there are different cameras. At the end of the conference, the first possibility is this. If it's too difficult for you, I give you a second possibility, which is also on the back of your badge. The second possibility is this. You decide what to do, okay? So Lucille, for sure, will say it. And there is a name for this award. At the end of the conference, the award will be the Golden Ugula Award for the best singer of the conference. Okay? You have time to think. I think now it's better to have the other scientific session before lunchtime. Okay. So we have different speakers, and also the chairman, please go to this table and chair the next session.
Okay. Silence, please. Silence, please. So we are coming to the first speaker. First of all, let me thank you for the very nice opening session, for the music, for Walter Kuchera's very interesting and spiritual talk. Okay, we are coming to the first presenter, which is Laura Katting, who will present us a new system for REM pyrolysis oxidation, 14 CO2 analysis of sediments.
Yeah.
Please go on, 12 minutes.
Yeah, thank you very much. Welcome everybody. My name is Laura Katting. I'm a PhD student at the Alfred Wegener Institute in Bremerhaven. And as part of my PhD project, I'm establishing a new method called REM pyrolysis oxidation in our lab. And today I will show some of the most recent progress that has been made in this project, and I will also show some of the first results that we received for an interlab comparison that we initiated. But first, I would like to talk very briefly about the method itself. So what is REM pyrolysis oxidation? Pyrolysis itself refers to the thermal degradation of a substance in the absence of oxygen. In our case, that substance is sediment that has been acidified to remove any inorganic carbon. And this sediment is then heated from 25 degrees to about 900 degrees, which leads to the formation of volatile pyrolysis products, which are subsequently oxidized to CO2, and then this CO2 can be radiocarbonated, either as gas or as graphite. And what you see here is, you can't really see the pointer. Well, anyways, on the left side, you can see the result of a typical RPO run. It's called a thermogram, and what you see is the CO2 that is developed in dependence of the temperature. And the underlying assumption here is that labile organic matter that has a lower thermochemical stability will react at lower temperatures and also form CO2 at lower temperatures compared to organic matter that is more stable and will react at higher temperatures. So based on the shape of this curve, we can identify fractions of organic matter that have distinct characteristics. And if we manage to trap the CO2 from this fraction separately, we can then radiocarbon it separately, and in this way we receive multiple radiocarbon ages for one single sample. And what we typically get is the stepwise increase of the radiocarbon age with the temperature. So the radiocarbon age of a fraction collected at higher temperatures is usually much older than that of a fraction collected at lower temperatures. This is the very first RPO machine that was built in 2003 at the Woods Hole Oceanographic Institute. It is now located at the University of South Florida, and it served as the prototype for the 3 systems that were built in the following decades at NOSAMS in the US, in New Zealand, and in Northern Ireland. Then 2 years ago, the MPI in Jena bought a commercial machine. It's the same one that we are also using, and they modified it for ramped combustion. So they don't pyrolyze the sediment, they combust it. And then last year, the Knife Radiocarbon Lab introduced their system. It's also a customized system that they built themselves, but it's different. It has a different setup than the other ones. And they also use it for ramped combustion. Apart from these, let's say, established systems, there are also 2 machines that are currently being developed. One is at the ETH in Zurich, and one is our system at AVI. Here you can see the main part of our system. It's a commercial machine we bought from Elementar. It's called a Solitok Cube, and it's initially used to separate different species of carbon within one sample. This is what the inside looks like. Behind the shield, the center part, there is a quartz glass reactor that is located inside 2 furnaces, an upper pyrolysis furnace and a lower oxidation furnace that is filled with an oxidation agent, in our case that is copper oxide, and a platinum catalyst. On top, you can see this round, darker little thing. That is where the crucibles that contain the sediments are located. And then the upper rising part is the autosampler. The autosampler grips one of the crucibles with the sediment and then lowers it into this pyrolysis furnace. and this upper pyrolysis furnace is also that part which is dynamically heated. The pyrolysis products are carried with the gas stream down to the oxidation furnace. They're oxidized to CO2, and then the CO2 passes from here through this chemical that contains brass wool. Is it working now?
Yes. Just a second.
It's fine. That removes the halogens, and from there the gas stream goes into the water trap, and from there to the back of the machine where there is a CO2 detector. To the outlet of the machine, we have connected our self-constructed zeolite trap system. It consists of... Now it's working? Thank you very much. Yeah, no. Okay, it doesn't matter. It consists of 8 identical zeolite traps that are connected to a multi-position valve. And the whole system can be decoupled using this red quick fit connector. And this quick fit connector is gas tight when it's closed. But during the coupling and the decoupling process, because we really push it manually inside of each other, we always introduce a tiny amount of oxygen from a tiny bit of atmosphere into the system. And that's why we have the so-called waste trap. It's completely identical to all the other traps, but we guide the gas stream over this waste trap during the coupling process to avoid contamination of the fractions we have already trapped on the zeolite traps. This is what the system looks like in the lab. You can imagine the Solitox standing right next to it. And then the gas enters here to this 3-way valve, either into the atmosphere or through this tubing. And here you see the quick fit connectors onto our zeolite trap system. And then we can use this little remote here to choose the pathway of the gas. So if we conduct a pyrolysis run, we identify the fractions we want to separate, and then we use this little remote to guide the gas stream accordingly over one of these traps so that we can trap every single fraction on an individual trap. Once the trapping system is loaded, it's deconnected here and here, and then we carry the whole loaded trap system to our AMS machine, which is a Micadas. You can see it there in the background. And then in front of the Micadas, we have this ramp system. Here, inside of this little hole, you can see the outlet of our hot air heater that is used to liberate the CO2 from the traps. And then we have several little hooks here that we can use to move the trap up one step if we want to measure the next trap. So now you can see the heater is working completely. We reach 400 degrees in about 1 minute. And this heating process then liberates the CO2 from the traps, and the CO2 is carried from the traps through this tubing into the gas ion source interface from the Micadas, and from there directly into the gas ion source when we do the 14C measurements. Now, the fact that we measure our 14C as gas, our CO2 as gas, and that we use it in combination with this zeolite trap system saves us a lot of time, because we don't have to graphitize our samples and we don't need a secondary combustion step. So if I get a sample that I want to analyze and have never measured it before, I need to conduct 2 pyrolysis runs, one to identify the fractions and then one for fraction collection. and then we need 15 minutes 14C measurement time for each fraction. So let's say if I trap 6 fractions in one sample, that would come up to a total of 4.5 hours, including the measurement time. So if I can load both trap systems the day prior to the measurements and then continuously load the system that is not currently being measured, I can measure up to 33 fractions per day, which equals to about 2 to 5 samples. Here you can see a typical RPO run that is generated by our Solitalk. The Solitalk can do both combustion and pyrolysis. We usually use it in pyrolysis mode. But even in pyrolysis mode, there is a time towards the end of the measurement here where the system introduces oxygen to burn off any organic material that cannot be pyrolyzed. So we create this non-pyrolyzable peak, which is usually the highest peak in the thermogram. We create it always, and that's regardless of the nature of the sample. Here you can see the first results of our blank determination. To do this, we pyrolyzed different masses of a modern and a fossil standard, and then radiocarbon dated the 14C. And then the 14C values are plotted over the inverted mass, and a Bayesian linear regression model is applied to calculate the blank, which is determined by the intersection point of the 2 linear regressions of each standard type. And in this first attempt, we achieved, or the result was a blank with a mass of 3 micrograms of carbon and an F14C value of 0.46. And with this initial blank, we could then start to think about an interlab comparison. Here you can see some characteristics of the systems that I introduced to you earlier. This letter here denotes which reaction type pyrolysis...
1 minute.
Oh, 1 minute. Oh, sorry. Okay, I'm going to skip through that a little bit. Anyways, let's just say the ABI and the ETH systems are the only ones that use zeolite traps instead of cryogenic traps. And our blank is in the overall size range that has been published in the literature so far. For the lab comparison, we sent out different sediment types to the labs and asked them to return the thermograms and asked them to measure and blank correct the data. They would measure anything in their labs. And now I'm going to quickly show you the results of the Cow Creek and Arctic sediment that we sent out. Here are the results of the Cow Creek. What's really important here is to see that the thermogram from NOSAMS and the thermogram from New Zealand, they look very similar. And this is in contrast to the thermogram that we produce, which looks not only different in shape, but we also produce CO2 until a much higher temperature, until about 900 degrees. And if we look now at these results here, at the F14C results, we can see that we see a similar trend at the different labs, but there's a substantial difference in the individual ages we got for the fractions. And one hypothesis is that this is caused by the amount of oxygen that is included in the gas stream. I'm going to skip over this. These are other results, but I'm going to skip them now. Here you can see the thermograms we got for a different type of sample, and in order to investigate this hypothesis about the influence of oxygen, we decided to do some more experiments with this sample. This is our thermogram in comparison. You can see the shape is really different, and we have this super large non-pyrolyzable peak. And what we then did is we installed an oxygen sensor in the gas line, turned off the oxygen supply to the machine almost completely, and then started a combustion run. So not a pyrolysis run, a combustion run. The oxygen sensor measured the oxygen concentration in the gas stream to be about 0.1%. And this tiny amount of oxygen in the gas stream shifted our thermogram from this one to this one. So it basically replicated the thermograms we got from the other labs. And it might not be so surprising to receive different results when you use 2 completely different methods like pyrolysis and combustion, but at least to me it was extremely surprising to see the magnitude of this effect already present at this low amount of oxygen. This brings me to my summary. We have established a working RPO system with a robust set of standard operating procedures at AVI. We have a low procedural blank, and we are now basically ready for routine operations. And as a first result from the interlab comparison, we can see that the amount of oxygen has an extremely high influence both on the shape of the thermogram but also on the radiocarbon date we receive. That concludes my presentation. I would like to take this opportunity to thank the project partners for their interest in this interlab comparison and for the time that they have invested. It's much appreciated, and we're really looking forward to receiving more data to fill in some more of the gaps.
Thank you very much. Well, if you want to do the completion. Thank you for your very interesting talk. Let's say one question because of the low amount of time, if there is. If not, Elisabeth.
Mm-hmm.
Not the background and not the oxalic or the standard. Do you have some results that you reproduce?
We have results. I haven't plotted them here, but we have measured one sample about 70 times, and we have a really good reproducibility. Unfortunately, I would like to show you the plots to prove that, but we have definitely looked at that, and this is one of the main concerns, to be able to reproduce our measurements, but that's one of the advantages of a commercial system, that it's much easier to reproduce the data.
We can continue this during the lunch break.
Yes.
Okay, let's continue to the next speaker. And thank you. This will be Mr. or Mrs. Bolandi. Mr. Bolandi, Organic Matter Dynamics in those lumps, Insights from Online Ramped Oxidation, 14C Analysis. So we keep the methods.
Okay. Hello everybody, I'm Marco, and today I would like to bring you to a small journey specifically on the organic matter present in the permafrost and in the thaw. Something similar, a work that we did similarly to what actually Laura presented. We will use actually the lability of the organic matter inside of the permafrost and use this in order to analyze the 14C. So, thank you very much, Laura, for your great job in presenting. First, I think you're pretty familiar with this plot, and personally, I'm quite interested in the permafrost. You will see why, and you will also understand that it's quite serious to look at this. The thing is, the advantage that I have is that the permafrost has also a lot of organic matter. And the thing is, we can use radiocarbon to actually date the turnover time. The thing is that on one hand, we can either use compound-specific methods, and these are really precise and really good in picking specific compounds. But often they are labor-intensive. On the other hand, you have the bulk measurements, and they are really great because you have an average. And as you could also see from Laura's presentation, well, it's not totally true because the average doesn't tell us what's actually happening. So, how can we resolve this? It's actually through differentiating the organic matter by, for example, in our case, the thermal lability. We at ETH, we did a similar setup, but we actually worked through the online ramped oxidation system, the double trap interface, which was developed together with Daniele De Maria and with the IMS, low energy IMS. I will specifically focus for these talks and for the time only on the online ramped oxidation. So, and my colleagues tomorrow, please go, they are really great people, go to their presentation at 11 and 11:12 for the double trap interface and the layout. So I skipped that part. What is actually Oro? Oro is a combustion oven, and it has two ovens. One is the combustion oven, and the top part has actually the ramping oven. Here you can see it contains actually the silver instead of platinum and copper oxide. We go actually with a really high concentration of oxygen inside and helium, and also with a strong flow. You will see that there will be difference, so every RPO setup has its own thermogram, and it's also important for the internal reproducibility to understand this. Finally, there is the CO2 sensor, and then the double trap IMS coupled. I remind you, just go to Daniele for better understanding the double trap interface and the Lea for URS. So, clearly I'm more interested in the organic matter, not the inorganic carbon. So we usually remove it by doing fumigation. Then in order to get 1 to 0.3 milligrams of carbon, we have roughly 30 to 50 milligrams of material. And finally, this is what I do. And you can actually see here a bunch of data that I measured, and these were actually 2 samples. Usually I do 2 samples a day with the different fractions. So, why do we care actually for the permafrost? The example that I wanted to show you. So, it's 1,500 gigatons of material, and you also know that this is roughly twice the amount in the atmosphere. But the Arctic is actually warming twice as fast. That means that we have huge puddles or thawing permafrost, which are creating positive feedback because you have organic matter which is decomposing. So, how does it look like? Well, here we are close to Yukon. We are in the Yukon, northern Canada, northwest Canada, Alaska, and we are in the First Nation lands. And all the gray dots are actually all those slumps, how big they are and how they look. So this is actually an aerial view. And this is a 6-meter wall, head wall, where the top part is the active layer, 6 meters of exposed permafrost, debris, which then runs off to the Peel River. So this huge thingy actually became, it's only 25 years old, not the carbon that we will see later. This is roughly, so I did an estimate using Google Maps, this is roughly 4 to 6 times the castle that we are in, just to give you an approximation. And this is one of the gray dots. So, how do the thermograms look like? So, as you can see, the permafrost layer, debris, and runoff, they look pretty similar, while the active layer has more material coming out, but it doesn't have the same shape. Okay, that's a good indication. So we know that actually permafrost, debris, and runoff are connected to. But how does it look like with the 14C? The 14C shows clearly that, as expected, the permafrost layers and runoff, they are actually in line, while the active layer is pretty flat. Even though being old, it's still consistent. So the thing is, interestingly, we have this age, but that means that the material that it's coming out, it's mostly also going into the river. While the active layer, which I would like to remind you, is also the more richer in organic, it doesn't show to being a big import into those runoffs. So, what could we understand? We could separate the organic matter that we had from the permafrost simply by using a simple technique, using the heat as well. And we measured different fractions. So that's already a big step. We showed differences, and we could see that the active layer, which is the more biological rich and has more organic carbon, shows actually more material at 400, 450 degrees. Finally, the runoff has an age which goes to the Holocenes, which goes towards the direction of the permafrost, or the permafrost layer, which makes sense. But the question is, what's actually inside? So for us, we know that the permafrost is releasing a lot of material, but it looks like it's being transported. So the question will be, what's actually the material inside in these different thermal fractions? And to do this, we would like to use the GCMS using the temporal fractions. I would like to thank actually my mentors and the people, some of them are here, and the technical support, the fundings, and in particular also the University of Salento and SEDAC to inviting me and being the second speaker. That was really kind. Thank you very much. And whoa. Anyways, so one more thing. So please, if you have time, drink the coffee, the LECCE coffee. And it's the iced coffee, and it's really, really nice. So please enjoy this. Thank you very much, guys.
And now, volare.
Volare, oh, cantare, oh.
Thanks a lot for your talk, and you were pretty much in time, so we have time for a few questions. Alex?
Did you estimate any cross-contamination between fraction after the zeolite trap?
Thank you very much. That's really a good question. We didn't see any cross-contamination. We didn't see any cross-contamination that we could say, yes, there is there. And maybe Daniele Della Maria will tomorrow talk a little bit clearer about this. But we saw that by reproducing it, we repeated a few times the test, and actually it was consistent with what we were having. Furthermore, we had also the bulk measurements, just to make sure that we were not screwing it up. And we could see that actually the weighted average, which I didn't put on it, was actually consistent with the bulk measurements that we got. Does it answer your question?
No, actually, from our experience with age, everybody do pre. Pre. Combust samples and go to the lead trap and throw it away. And when we try actually estimated, we have a few promille contamination if we don't do this. So you don't have this possibility to do pre, actually throw away some fractions.
So we
do it twice.
So we do actually the cleaning in the traps. So each time we are cleaning with oxygen and helium. So we are flushing, and then we don't have any signal afterwards. Does it answer?
Thank you.
Thank you.
Maybe we can go on. Somebody else? Some more questions? Quasiara?
Hello.
Hello. Great talk, Marco. Maybe you had mentioned, but what method do you use when you were producing the thermograms? The previous talk mentioned that you use a little bit of oxygen and that changed the thermogram. And I wonder if you had a mixture of oxygen and helium as well. So, and how much was to produce these profiles?
Yes, thank you very much. That's actually a really good question. Also, what Laura was pointing out. In our case, we are using 18% of oxygen mole inside of helium, so we are relatively in high concentration. The thing is, when we work, so the next step, we are actually comparing with the university AVI to see what's actually happening. We could already see, in our case, that inside, so the internal reproducibility is there, but when we want to actually do it compared to the nosams, which are using pyrolysis, we need to adjust, for example, the oxygen amount and lowering, or also the masses. The other thing that I would like to point out is also that it's never good to do a peers to apple comparison. So sometimes we need to be careful that our setup is one way and the RPO is another way. So that must be really clear. So clearly it's always really good, but yeah, that's just something that is always in my mind, just to say.
Thank you.
You're welcome.
Elisabetta?
So, because you're talking about ramping,
yes.
Do you think that this reaction is thermodynamic or kinetic? Like, how do you decide the time of ramping the temperature? Because the peaks are not separated. So somehow it seems that you might have a contribution of two different fractions, or am I wrong?
Yes, that's actually a really good question. So there are few factors that we need to consider while we do actually the ramping process, and that's actually when we look at the temperature rate. And fortunately, we can also toggle it to make sure that we are trying to deconvolute better the temperature, the kinetics. So the thing is, it depends a lot also what you want to look at. Clearly, in my case, because I wanted to show you the permafrost and how it's actually evolving, in this case we thought, well, we will go with the ramping temperature, which is consistent between all the different samples that we are doing right now. But in this case, we decided to go with the speed that we selected that was ideal to show the fractionation in this case. But you make actually a good point. Any other questions?
So I think we are finished for now. Thanks for the two speakers for their contribution. And it seems and I just heard that the last speaker for this session, Madame Tisnera-Laborde, will not give this, so it is removed. So we are now proceeding to the lunch break. So I wish you all a good pause and bon appetit. And we will come back 1 p.m. here. Try to be straight so that we can start right on time.
Let's move from the sediments we talked about this morning and go to atmospheric aerosol. Maybe most of us are very well experienced with such material, but let me just summarize the main feature of this kind of particles with the name atmospheric aerosol, or with the name particulate matter. We typically intend all those suspended particles in atmosphere. They can be solid particles, they can be liquid particles, but what all of them have in common is the dimension. They are very tiny, very small, and in particular, the most important for us are the smallest. So PM10 or PM2.5, PM1, because as the smallest they are, the, let's say, most dangerous or interesting for the effects they can have, they are. Their typical concentration in air, there are many different situations we can find, because it's true that we can find particulate matter also in remote sites, like for example Arctic or Antarctic. But we can, of course, find particulate matter also in very crowded contexts, like, for example, cities or deserts or other places where we expect a much higher concentration. Okay. Sorry. Okay, so they are produced in primary processes, but they are also produced as a result of secondary reactions. So there are some, we can recognize some physical sources emitting particulate matter, but we also have to acknowledge that all the concentration of particulate matter we find in the atmosphere is not due only to primary processes, but also as a result of something different. So compounds already present in the atmosphere that react coming to, again, particulate matter. As for the direct processes, we can recognize both natural processes, like for example, the marine spray, eruptions of volcanoes, the mineral dust from the desert wind, and also the combustion of biomasses. But of course, when we speak about particulate matter, also the anthropogenic processes are very important, because they can be emitted, for example, by combustion of fuels, both in factories or also in, for example, in cars. And they are also emitted by, for example, very common operations such as switch on or lighting the oven in our houses. So why PM is so important? First of all, they are important because a high concentration of particulate matter in atmosphere can affect our Earth, because they can be inhaled, and a prolonged inhalation of such particles can provoke lung cancer, also cardiopulmonary diseases, and can also affect mortality. But they have an important role also in the environment, and also for the global change. Actually, well, I'm not an expert, but I know that the real role of particulate matter in atmosphere forcing and affecting the global change is not clear yet. So there are several parameters to understand, and actually there is no consensus till now whether they have a positive feedback on the changing of climate or a negative feedback. So anyway, in order to try to solve this ambiguity, is important to measure and to understand their role. Okay. Particulate matter is composed of maybe all the elements that are present in the periodic table. Now here I will focus on carbonaceous aerosol. So carbon element and also on carbon compounds, because it typically represents the largest component of all the elements present in the PM that we can collect, because about 50% of particulate matter in urban contexts is made of carbon. Of course, it is present in many different chemical and physical forms. I'm not an organic chemist, but I know that the possibility to arrange these three simple elements, such as carbon, oxygen, and hydrogen together, are almost infinite. And we can find all these infinite combinations in particulate matter. Here you see the, let's say, basic equation for the total carbon present in the particulate matter, because we can consider it as the sum of the element, what is called elemental carbon, organic carbon, and partly carbonate carbon. I will neglect in my presentation the carbonate carbon, because here in Italy its presence is less important than elemental and organic. The two types of particulate matter are different with respect to their optical and thermal properties, which means that, of course, the elemental carbon, which is also called black carbon, is characterized to be very, let's say, powerful in absorbing light. And as for the different thermal properties, typically organic carbon evolves at lower temperature with respect to elemental carbon. As I told before, there are different emission sources, and here we have the main principal emission sources for both elemental and organic carbon, which are the wood burning, the natural emissions due to, for example, wind erosions or something like this, and also the combustion of fossil fuel. So it's clear that if we would like to understand the role of such carbonaceous particles for the health and also for the global change, we have to identify the emission sources. Because only if we identify the emission sources, we can improve the global change models, and we can also contribute to arrange pollution abatement strategies. I mean, it's true that a large part of elemental carbon, for example, comes from combustion of fossil fuels, and we know that. But it's important also to understand if this is the main emission source, or whether there are other important contributions, because some contribution can be lowered, some others, unfortunately, not. So radiocarbon by itself cannot tell all the story about the source apportionment, because we have to deal with the different techniques if we are interested in different elements. And for example, for sure, we have to combine other physical techniques such as ion beam analysis, PIXI and PIGI, but also some chemical techniques just to identify and reconstruct as much as possible the situation of our particulate matter. But now I will focus on radiocarbon, and what we can say is that we have to do some source apportionment for radiocarbon. We can either measure the total carbon or the EC and OC separately. Of course, it depends on our technology, let's say, and also on what we are interested in, because we can use a simple two sources model measuring the total carbon, and in this way we can estimate fossil versus modern contributions, or we can measure EC and OC, and we can apply a three sources model, and in this way we can estimate the natural versus anthropogenic sources. As I wrote here, pay attention. In the three sources model, we don't know everything. I mean, there are some parameters that are still, let's say, undefined. There are several papers describing and estimating them, but we really need to do some more works to establish these parameters. Which are the challenges if we would like to apply radiocarbon to such material? Well, PM is typically collected on filters, and here you can see a typical quartz filter on which the particulate matter has been deposited. Of course, we have to use materials for the filters that is transparent to radiocarbon, and the choice is, of course, quartz. When interested in applying three sources model, the organic carbon has to be separated from the elemental carbon. And this is not trivial, but this is really tricky, still tricky, because there is still debate on the most appropriate thermal particle for the separation. We can apply different temperature in oxygen and or helium atmosphere, but there's still no consensus on which recipes we have to apply, and so this is also a challenge for the future. And masses are very small, because if we are interested in PM10 or even in PM2.5, our quantity, our mass on the filter is not so big. And in addition, you see here a filter, okay? But as I told you before, our interest is to apply different techniques on the same filter just to reconstruct all the story of the particulate matter. So not only what about carbonaceous particles, but also what about, for example, silicon, aluminum, and all the other heavy elements. So typically the filter is, each filter is divided in 3-4 parts, and each part is dedicated to a single technique, a single measurement. And of course, the mass on the filter depends on the place where you are sampling. Because if you are in a remote site, you don't have a lot of particulate matter. If you, well, you see here, this filter is very dark, because it was collected in an urban context, so where you have a lot of particulate matter. But things change if you go to a remote site. And things change also if you are interested not only in total carbon, but in the separate organic or elemental carbon. So it's important to have a reliable way to deal with small masses. And of course, all of us knows that there are different approaches that we can use. We can use gaseous ion source in the AMS beamline, or we can use solid sample sputtering ion source. This is a very simple model of our accelerator in Florence. It's a typical configuration, an NMS typical configuration made of 3 M-volt tandem accelerator. It is not a dedicated AMS machine because we have to share beam time also with IABA people, but okay, this is okay. And we have a solid sample sputtering ion source. So we have to deal, yes, with small samples, but with solid small sample. And what I would like to underline is that in our configuration, I can say that we are happy to have a solid ion source, in the sense that this source allows us to perform multiple measurements on the same sample. So we typically insert a sample, measure for a while, then go to the subsequent sample and go on, finish all the batch and start again. So in this way we can monitor the stability of the accelerator and of all the beamline for periods up to a few days. So here I present you Miss Marple, and Federica, who worked with us, invented this name that I find it very wonderful. So this is the Milan small sample attenuated radiocarbon preparation line, dealing with samples collected from particulate matter on quartz filter. So here we have, you read this sketch from right to left. So in the upper part on the left, we have the feeding with helium and oxygen that are first purified and then enters the main oven. So filters are inserted directly in the main oven. Then the CO2 evolving travels along the line. First travels across a sulfur and halogen strap. Then there is a succession of 2 thermal traps made of liquid nitrogen, and the different temperatures are achieved by changing the relative position between the coils and the dewar with liquid nitrogen in. So in the first trap, we collect the water and the nitrogen oxide. Then we first trap the carbon dioxide. We collected from the sample. We trap the CO2 to get rid of helium along the line, and then we transfer the carbon dioxide to either one of the 2 reaction chambers. So here I summarize most of the characteristics of this beamline. Of course, we are using materials that are intrinsically clean or that can be cleaned very well to be used in radiocarbon setups. So we are using quartz, stainless steel, calrets. Calrets is polymer used for O-rings, and it's similar to Viton. We are most used to Viton probably, but it's very interesting because it is characterized by a very low degassing rate, even at high temperature of 200 to 250 Celsius degrees. Of course, we are using high purity gases, and also we are monitoring the CO2 that is evolving from our samples by monitoring the combustion process with a non-dispersive infrared detector. Graphitization is achieved by the Bosch reaction, so reaction of carbon dioxide with hydrogen in the presence of iron as a catalyst, and to deal with a very small sample. Here you see some photos of Miss Marple. In the first photo, you see there the main oven, the traps made of consisting of the liquid nitrogen dewars, the first trap for water and nitrogen oxide, and then the trap for CO2. And here you see our small reactor optimized for about 50 micrograms of carbon samples. So the idea is to let's say, perform the reaction forming graphite directly on iron already pressed in such a small copper inset. So we first press the graphite on the small copper inset, start the reaction, and then transfer the copper inset with the graphite on in our typical, here, I don't know if people sitting on this side can see in the bottom part, in our typical aluminum target holders for our ion source. So, yes, some notes to finish with. Reaction rate, it's not so, well, it's pretty easy to deal with such small samples. But we have to keep in mind that, for example, a standardization of the procedure is really important to have a very stable ion current along the EMS beam line in the accelerator. And the standardization of the procedure already starts in the graphitization step. So, for example, we have experienced that the reaction rate for graphitization depends on how much strong the iron has been pressed. And the reaction rate also influences our, let's say, typical beam currents that we are extracting from the sample in the ion source. So it's, I think that it's really important to be in stable conditions when we measure in the accelerator, but as we all know, these stable conditions start well before in sample preparation laboratory. Of course, on the EMS beam line, attention is focused on alignment of sputtering position with the ionizer, and here in the graph you see a sort of scan of the current both 12 and 13C we can extract with respect to different position of the ionizer with respect to the sputtered graphite. So, working with the new line, we checked, of course, the reproducibility by measuring primary standards. We checked the background, and you see here the background is not so beautiful. We have in mind archaeological applications, but we are dealing with environmental particulate matter samples where the precision needed is somehow not so important as for archaeological application. And of course, we also check the accuracy on secondary standards. So, for example, measuring C7 standard and also particulate matter standard. Well, as respect with particulate matter standard, I have to say that it's not easy to check accuracy because actually there is no, till now, a real standard reference material for particulate matter. There can be some hints from, for example, the last intercomparison campaign we performed almost 10 years ago, probably. Some of us can remember. Oh my God, sorry. Anyway, so this is an invite. Let's try to find a consensus material for second standard reference material. Okay, so this is an example from the campaign. What next? The line is fully in operation. First measurement campaigns have been carried out, but we can improve the precision and we can improve the background for sure, and we have still to address the further challenges of aerosol source apportionment. And thank you.
Unfortunately, before of
That's all. Thank you very much. I will put a good word with the people deciding for the award, okay? For you.
You use up all your time.
Sorry.
Some time from
Sorry.
other people. And no question. Sorry. If somebody wanna ask, you can ask her in a break. And the next presentation is method from
Yes.
Biogas. Okay, interlaboratory comparison for the C14 measurement of the biogenic carbon fraction in biogas and blends of biogas and natural gas.
Thank you. Yeah, good afternoon, everybody. My name is Harro Meijer. I'm presenting this on, also with all the co-authors that you see here, and all have been working on this project that you see, a Euromed-funded project called Metrology for Biomethane. And this was a part of it. And of course, the whole interest in biogases and biomethane especially has everything to do with the energy transition, with our worries about climate. And I think in this group, I do not have to explain that much further, except that there is nowadays also quite a lot of, say, legal and economic interest in this, because of the European the energy CO2 emission schemes. You have to pay if you bring fossil CO2 into the atmosphere, but not if the CO2 can be pointed to be of biogenic origin. So this is no longer just a scientific effort, it also has to do with economy, and as soon as economy comes into play, you need standards and you need legal things and so forth. So this whole metrology for biomethane also had those aspects. But we, as simple radiocarbon people, didn't care too much about it and just wanted to see what we could do finding the percentage of biogas in a biogas natural gas mixture. So I will show a bit of this, the background. I will show the pre-treatment of the biogases and the mixtures and how differences in that can make differences in your result. Show the results, of course, and then some conclusions and outlook. All right, the principle would be no real surprise here. The 14C method for biofossil determination is simply determining the 14C content of a sample. You compare it to what 14C from a pure biogenic origin would be, and the fraction, the ratio of those is simply your fraction bio. Simple enough. And for renewable materials like the junk, the wastes you see here, the radiocarbon is of course very similar to recent atmospheric 14 CO2 values. So the fraction that you got out of this very simple formula is 1, or if you will, 100%. On the other side, fossil material doesn't contain any 14C anymore, and you will find FBio to be 0%. And the strength, of course, in this, the unique strength of radiocarbon is that only radiocarbon offers this very high 1 to 0 and very unambiguous selectivity. People have been trying simpler methods, but they will never score as good as radiocarbon. So this is not a surprise, this is not new, it has already been widely accepted, and you can see that by the list of the existing standards. So here you see STOF, general bio-based products, has a European and an American standard. Solid recovered fuel has a special one, flue gas has one, for plastics and for rubber. All are standards. And from a C14 point of view, you would ask, why on earth do you need so many standards? Well, that's how this legal stuff works. You have to describe again and again how the C14 method works, and more especially how you have to pre-treat your samples in order to get to a good result. And that is also the reason why for these biomethane or biogas fuels, we need a new standard. The principles, of course, are the same, but the practical process of pre-treating gases is not well covered by any of these existing standards. And that was one of the subjects of the biomethane project. The rest was about trace elements inside the biogas that could possibly waste the burning process or anything else. That was not of our concern. We had the part that had to do with 14C. So our task was to develop a 14C-based test method for fuel gases that contain methane, and for that we organized an inter-laboratory comparison for C14 labs. And requirements for the method are pretty simple, you would say. So the sample preparation should be suitable for all types of fuel gases. So of course methane, but also the non-methane hydrocarbons, so the higher alkanes, so to say. They usually also contain CO2. We have to also consider that, maybe carbon monoxide, maybe even other stuff. The requirement is that all of this needs to go into your final sample. All the carbon needs to be included in the 14C measurement, and this is vital, especially for mixtures between biogas and fossil fuel. And the quantification, of course, needs to be done like between 0 and 100% biogenic carbon. Right. Now here's the interlaboratory comparison. We produced a set of 5 samples. 2 were pure or allegedly pure biogases, original biogases from Sweden. And then the other partner made 3 biogas, natural gas mixtures out of this, aiming at respectively 45, 75 and 95% biogenic carbon, so the whole range basically. And collection was done by RICE, a Swedish organization. VSL, the Dutch Metrology Institute, did the mixture very carefully and quantitatively. And we at the University of Groningen finally packed all this and distributed it and collected all the information from the results. And then the sample preparation, starting from this biogas until a final radiocarbon result, was done by 4 experienced radiocarbon labs in Europe. RICE made a GC analysis of the original gases, and you see here biogas D, that's one of them, and biogas E is the other one. You see it's mostly methane, obviously. There's a bit of CO2, and biogas E is very strange because it also shows a little bit of these higher alkanes, which is very untypical for a biogas. So looks as if there has been an addition of 2 to maybe 3% or so of fossil gas. If you compare the column for the natural gas and multiply it by 0.02 or 0.03, indeed you would end up with values like in biogas E. Biogas D is mostly manure and 10% of other stuff, and biogas E is food waste and sludge. So both of them are very recent and short-lived material. Then the blue column, or the blue table here, shows the production of the mixtures by VSL, so very carefully done, such that we can determine the percentage of bio-C, so for all the molecules together, and you see the numbers that we end up to there. Then the 4 expert labs, I think, including me, 3 of them are present here. They have generally very different preparation schemes. Some of them were already dealing with gases before, others had to think how to do this, because usually we work with solids. So some collect really all of the hydrocarbons, others only some, and some did that on purpose, others did that accidentally. And some even split the gases into the various components, so they could do the whole and also the pure CO2 or the methane or the non-methane hydrocarbons and anything, and they did that purposefully. Some methods, however, select accidentally. And just to give you, I don't give you the details of it. Here are 3 of the labs with the schemes that, of course, they provided for this ring test, where you can see you can do all kind of tricks with cryo traps, with zeolites, you name it, and you can do different things to select only the methane, the pure gas, or the higher alkanes, or combinations of the like. And some are really accidentally not taking everything into account, and other ones are doing that on purpose. Right, so here's the whole table. You can see the carbon fractionation intended. If there is an empty space, it means there was no fractionation intended. Sometimes that worked, and all the carbon was indeed produced and given to the radiocarbon measurement. Others where it happened accidentally. And those 3 here really included all carbons. That was the intention. Now here's the result then for the full combustion, so the 3 that really show all the carbon included. The green ones are the biogases, and you see the values for gas D and gas E. These are the averages, and you see indeed biogas D is slightly higher than biogas E, or I should say it the other way around. E is a bit lower than D, and that indeed means that E has a fraction of fossil fuel there. And Rice actually found out that this facility producing biogas, they are allowed to, when the process is interrupted, to admix natural gas. And of course, when everything goes well again, they start with biogas again, but there is still a possibility of a fraction of natural gas, and indeed that was the case here. Now, based on these values and the mixture that we know very carefully, you can calculate what you would expect for the mixtures, and those are shown here. So B and C are based on biogas D, and A is based on gas E. Now, if you take a look here, you see that in general there is good agreement. You can also see that the reported uncertainties by the labs taking part in this ring test are probably too low, and that's not because the precision of their radiocarbon measurement as such is not good enough, but because the pretreatment brings in uncertainties that are not fully reproduced in the uncertainty that they provide. And indeed, gas E is likely not 100% bio. That was a side result, not intended, but it was kind of funny that that came out so well. Yes, so if you look at the various preparation routes, as I said, some collect all of the carbon-containing molecules, and others only some, and some do that on purpose, and some do that accidentally. And in this scheme, you see one of the mixtures, the one with 45 bio, the green bar to the left, and the measurements, that is the labs that supposedly collect all the carbon-containing molecules, whereas the 4 red points to the right, you see there is selectivity of the carbons. And again, some do it on purpose, others do it accidentally. And only the rightmost point here is the one where the methane really got isolated exclusively and on purpose. And you see that value, well, is in reasonably accordance with what we expect for the pure methane. The mixture in brown, where you have the mix of methane plus the fossil ethane and the fossil propane, would land somewhere where the brown curve is. So you see that 3 out of these 4 points, they kind of are dragged towards there. There is not a pure methane measurement, but there is certainly not a all carbon measurement either. So this is really something that came out of the ring test that we have to describe better for making this a valuable method. Right. As we all know, the radiocarbon content in the atmosphere changes over the course of the years. So the 100% bio level also does that, and it provides a systematic uncertainty. Here is the curve based on the Jungfraujoch, so the high Swiss Alpine station measured by the University of Heidelberg for decades already, as the kind of highest radiocarbon value that you will find in Europe. Right? It's the mixed high troposphere there. That's kind of the best value, the highest value, if you like. The blue one is from our station, Lutjewat, just north of Groningen at the Waddenzee coast, which is a background station, but it's a continental background station that stands for where usually the crops grow. So that's what is well possible that crops and all the materials that produce the biogas have as a content. Now what we do then, we realize, of course, the value that we choose depends on the average growing year. Well, the 2 biogases we have are recent. If you would have stuff from trees, for example, then of course you would have an average over a much longer period. But in this case, that is pretty specific. And it depends a bit on the region of growth. So these were European, these were Swedish actually, so we think these are representative. Now then the high-end value that we take is the April to October average of the 14C value of Jungfraujoch. That's the growing season average there. And the low-end value we take as the 14C April to October average of our Dutch station Lutjewald. And for the year 2018, that's the year where these biogas were produced, that's the range between 103.4% and 101.1%. So you see there is a bit more than 2%, if you will, uncertainty range there. And then we calculate the minimal fraction of Bio-C as the measurement minus 2 times sigma divided by the maximum reference value, and the max is of course the, the opposite, so the highest possible 14C measurement divided by the minimal reference value. And that gives the range of this method for the bio percentage of such a gas. Now, then I already showed the results in terms of radiocarbon, but now I'll show them in terms of the fraction bio. Here's what you get for the two biogases, number D and E. You see this 14C value repeated again. You see they're systematically different, because the uncertainty is something like 0.3%, K equal to 2 sigma. If you then calculate the bio fraction, you see these ranges, or if you express them as a value plus or minus an uncertainty, you get 99.5 plus or minus 1.4% for biogas D, which indeed is fully bio, and for biogas E, it is a bit of like 2% lower, 97.3. So once again, indeed, there is still a tiny bit of fossil fuel there. Yeah, so that's what I said. Indeed, gas E appeared to contain something like 2.5% of fossil gas, and that was properly detected. And if you then look back on the GC analysis, you see that the appearance of these non-methane hydrocarbons, the higher alkanes, indeed hints to the presence of natural gas, because natural gas always contains those, and biogases hardly ever. Quantification, however, would then be very difficult, because in the different natural gases, these NMHCs vary. But they give a hint. Now, and here's then the result of the ring test. So for mix A, B, and C, you see the fraction bio 72, 94, and 45, as kind of expected. Look at the uncertainties that we get from the value. So one would say this is a very reliable and accurate method for fuel gases containing methane or methane and other hydrocarbons. This works. And the uncertainty is better than 2%. And the majority of that uncertainty is systematic. It is, by definition, caused by the 100% bio value that we take. What is crucial, and that was indeed also this ring test showed, sample preparation methods should really include all carbon, including the CO2. Even though the CO2, of course, doesn't take part in the combustion, it is still emitted to the atmosphere, and for the atmosphere, CO2 is CO2. So that also should be in this total package of bio fraction. And what we saw is that not all, even the experienced radiocarbon labs, are per definition, say, prepared for dealing with biogases, which is logical because their preparation lines are simply not made for those, or at least not for all. All this can lead to a design of such an ISO standard, which is, of course, similar to the other ones. Only the preparation part should really be defined differently here. So we are going to write a test method for 14C-based verification of biogas, biomethane, mixtures of natural gas with unconventional gases and renewable gases. That's a whole line, but these legal documents like these very specific long titles. And it should also be applicable for other fuel gases containing, well, one hydrocarbon or mixtures, or even mixtures with CO2 and CO, as I just explained. They have a lot in common with the existing 14C-based standards, like the definition of the 100% bio, which is crucial for the method, of course. And also, I didn't pay attention to this, but measurement precision, including the pretreatment, is a thing. And also a thing that I didn't mention, the carbon-13 correction is a bit tricky if you mix fossil with bio, because fossil, after all, doesn't have any C14, so correcting with the carbon-13 value for fossil corrects the bio part, whereas it shouldn't. Anyway, we published on this a couple of years ago. What is different That is the sample pretreatment. So we have to prescribe a way of performing and testing complete conversion of all the gas components. Yes. To finish, I decided not to sing because the contrast with the fantastic music this morning would do pain in your ears. So instead of that, I present a cartoon by a Finnish cartoon artist who makes a lot of cartoons on energy transition, environmental issues, and is worth looking at. And this is the one that is appropriate here. Thank you.
We have time for a couple questions. And there is somebody there. Somebody.
Thanks, Haro, or should I say Volare? But we did a study on a wastewater treatment plant trying to partition the various carbon emissions, and we got a surprise. So I guess this is a cautionary tale in that we measured activities in, I think, some of the primary sludge in particular of 200 PMC, which we didn't have a great explanation for other than that it was likely to be 14C labelled compounds in the municipal sewage systems. And if you have a look at what's available, it's alarming. There are hundreds, if not thousands, of 14C labelled compounds that are available and which don't need any licence to import and use. And a lot of them end up in the municipal sewage system. So when biogases are made from wastewater sludges, there is the potential that they might contain such hot carbon.
Yeah, fully acknowledged, and it can even be worse. If you can make money, then everything is done, allowed or not. So you can even think about deliberately masking a mixture of fossil by adding a bit of radiocarbon. The only thing that helps us is that it is very careful work, and for industry who have to hide these processes, probably also still too expensive and too risky. But you're right, the accidental mixture of anything radiocarbon labeled would indeed spoil the method, sure. Yeah.
And Walter.
You mentioned biogas. Can you comment a little bit on biofuel? Because biofuel is something which is going to come, apparently. Yeah? Is that going to play a role in replacing fossil fuel?
Well, the role will always be minor in the sense that it will certainly not take over. We're talking about a few percent, which includes biogas and biofuel. But for example, if you think about aviation, I would not know anything else that can replace our kerosene than biokerosene, for example. Now, I'm not the brightest of all minds, no doubt, but still, that's one way that the biofuels go to. Biofuels are actually covered in one of the other standards already. Mm-hmm. Yeah, so that's done. I mean, our petrol here in most parts of Europe contains already 5% biofuel. Mm-hmm. Yeah.
Okay.
That's a very interesting presentation, and I want to add, when I work at Geochron, we have a case when houses in New Hampshire suddenly started to blow up, and they discovered it was built on the landfill. And not so far from this place was underground gas storage. And it was actually a case when they have to decide, is it come from landfill or from gas storage? Gas storage is certainly natural, and landfill is biogas. And it was about 75% of modern.
Yeah, right, sure.
Yeah, mostly landfill. Thank you.
I see you.
Oh, sure.
Yeah, can you, or do you have an idea about what kind of, or what level of uncertainty we can expect with this new protocol? You know, because the ASTM protocol set about ±3% absolute uncertainty for all the issues you were mentioning about the declining bond peak and the uncertainty in the fractionation correction. And they say that in your case you see ±1.4. So it's probably something around that value, ±2%, something like this.
The 1.4 is already the main source of uncertainty is the 100% bio level. And of course that uncertainty, its influence of that uncertainty goes down if the level of bio goes down. So that's why you see for the 75% 1.4, but it scales. And so yeah, I think it depends very much if you know quite well where your material comes from, like in this case. I think the 100% bio definition is quite reliable, whereas if you have no idea and there can be wood involved, then the uncertainty grows. There is nothing you can do there.
Okay, thank you very much.
Yeah,
Okay, thank you very much.
Yeah.
Are you gonna sing? Next presentation by Renata Joe. It's from Brazilian laboratory in Niterói. Is it correct? Thank you. And presentation is handling liquid biofuel samples for biogenic fraction determination at this laboratory.
Okay. Good afternoon, everyone. My name is Renata Joe, and I'm doing my postdoctorate research in the University from Bahia in Brazil, in the new radiocarbon lab called LAPAC. But I did all my postgraduate study in the radiocarbon laboratory called LECCE with Professor Akita Macario in Rio de Janeiro, Brazil too. And I continue work with her in some projects and research, but today I will talk about methodological work. One minute. And today I'll talk about methodological work, and thank you. In the big project we have in LAC called I use biofuel samples, and the name of this project handle liquid biofuel samples for biogenic fractions determined at LAC OFF. So we know the AMS technique. It's a great sensitive, precise technique and can use for determination biofractions and for such biofuels. And that can differentiate chemical identical material though the analysis of biogenic and fossil carbon. Biogenic source have contemporary isotope ratios atmosphere, so have radiocarbon, while fossil source, for example, petroleum, do not, because all the radiocarbon decayed. So we can use this technique to determine the biofractions, such as biofuels. In Brazil, we don't have an entity to monitor these biofuels. You do not have yet approved laboratory to monitor this product. And LAC UFF is the only radiocarbon laboratory with AMS in Brazil, and we try to help the government to improve this scenario because we have a lot of tax incentive to produce this biofuels or bioplastic, but we don't have inspections. So these two photos, LAC UFF, we have a sample preparation lab and single-stage AMS. And this is a photo from LAPAC, the new radiocarbon in Bahia, another state in Brazil. Now I will show you the methodology we use to do these biofuel samples. We basically choose 4 different types of fuel, common found in some cultures, gasoline, ethanol from sugarcane, B100 is like a vegetable oil, and diesel. We choose 2 groups, volatile and not volatile, with biogenic source and fossil source. The idea is cover all the different types of full samples because we have, how can I say before, a big project, and we work with full samples with very low PMC, and it's very important be accurate and precise. So basically the steps for preparation is 3. The first is sample preparation, the second answer the samples in accelerator, and the third is analyze the results. For the sample preparation, we have basically the combustion, purification of CO2, and the characterization. But for this, before the combustion, we have a handling process, and step is very, very important too. So basically the step is first sample handle for preparation, second is preparation of combustion tube and vacuum line. We have a combustion, purification of CO2, graphitization, and finally pressing the sample for measuring the EMS. So how can I say before, we have 2 groups, volatile and not so volatile. For example, diesel is not so volatile, and I can handle it using glass pipette, but the problem is when I have a very volatile sample and the glass will not work, what can you do? What can you use? So I test using glass pipette, automatic pipette, plastic and glass syringe, and I show the result of this test. So how can I say? I have 3 tests in this case. The first is the handling using glass syringe, automatic pipette, glass pipette, glass syringe. The second test was using temperature trap. In this case, I used liquid nitrogen at minus 196 degrees Celsius, and the second trap is minus 50 degrees Celsius. The third test, I froze the samples before do the vacuum in the line. I test using fumer hood and glove bag, because when I have, how can I say, very low PMC, when I froze the sample, for example, if I use liquid nitrogen, when I froze, it's possible, frozen together, the carbon present atmosphere, and for full samples with very low PMC, this can be a contamination factor. So only show the process, in this case not volatile sample, we have a combustion tube with reagent silver and copper oxide, and we have an inner tube, and I put the sample, in this case for not volatile sample, I use glass syringe. I weigh around 2.5 milligrams full sample, and I froze the sample. I can use liquid nitrogen trap or minus 50 degrees Celsius, and put in the vacuum line, to the vacuum, and seal with a blowtorch. For volatile sample, the idea is the same. I use the combustion tube with reagent silver and copper oxide, and I have an inner tube. In this case, with very volatile sample, I use glass syringe, and I froze the sample in a glove bag with a net atmosphere. In this case, I use nitrogen atmosphere, and I connect this tube in a vacuum line, do the vacuum, and seal with a blowtorch. And I do the combustion of 900 degrees Celsius for 3 hours. And after that, I purify the CO2 in the vacuum line. I use 2 temperature trap, and the gas, after purify, I transfer to graphitization tube and seal together a tube, and I do the graphitization. In this case, a zinc reduction. And when the sample are in graphitized, I press in some kettles and put in the wheel and measure in the MS. This is the AMS in like youth, and for determination the biogenic fraction, I use the STM D6860. Now I show the results. Only to remind you, I present 3 tests, 3 results. The first in random, the second in temperature traps, and the third is experiment I froze the samples. For the first test, I use volatile and not so volatile sample. I have a B100, is a biogenic source, and I use glass pipette, automatic pipette, and glass syringe. For automatic pipette, the result PMC was around 70. When I compare with the another test, the result was around 95, and the value spec is 94.5. So in this case, the automatic pipette were the worst. For Titolo is a fossil source. I use glass pipette, and the results PMC was around 1, and the expected values is 0 because it's a fossil source. When I compare with another result, automatic pipette and plastic ring, the difference is considered. For gasoline is a fossil source and very, very volatile. The result with automatic pipette was around 6 and 3, and the plastic ring was around 3, and glass pipette was around 2, and the expected value is 0 because of fossil source. And the best in this case was using glass pipette, but I have very difficult to manipulate this sample because it's very, very volatile. And I will show in the next test, number 3, I use glass ring, was the best result. For ethanol, it's very difficult to manipulate, and I use only automatic pipette, and the result was around 70, and the expected values is 100. For the second test, I use only not volatile sample, diesel and B100. In this case, I use glass pipette, and in this case, the temperature trap I test, liquid nitrogen and minus 50 degrees Celsius. For B100, the results, the liquid nitrogen and minus 50 degrees Celsius was not so different, but when because the expected values is 94.5, but when for the diesel is a fossil source, when I use temperature trap minus 50 degrees Celsius was slightly better than the nitrogen, like nitrogen. For the third test was the experiment where I frozen the samples before do the vacuum in the line. In this case, I use glass syringe and I use only gasoline because very volatile and fossil source. In glove bag was the best, and when I compare the formaldehyde, because the PMC expected was 0. So for conclusion, now we have 2 new protocols for liquid samples. For volatile sample, the best was use glass syringe and freeze with like nitrogen in a glove bag. And for not volatile sample, the glass pipette and temperature trap minus 50 degrees was the best. So how can I say before? We have collaborated with some company and they send full samples with partial with biofuel and very, very low PMC. So it's very important we have accurate and precise. And so in order to, the idea is to cover a wide variety of fuel types and their variation, mainly for fuel with low PMC. So I'd like to thank everyone here and some agents helped me. and he's some reference I use. And this is, thank you so much. And sorry I'm nervous, but it's okay.
Thank you. Okay.
Oh, volta. Thank you.
Yeah. That was a very interesting presentation, and we have time for the questions. Any question? No, okay, I will start. I have a question. You show us ethanol, which has something like 70% of mother.
Yes.
How it's come from? What's the origin of this ethanol?
It's from Brazil. The PM6 pipette was 100. And because automatic pipette we show a very, how can I say, contaminations, no work in biogenic source and fossil source, the contaminations.
Do you think this ethanol was growing in a field, or it was a mixed synthetic ethanol from petroleum and natural?
No, it's biogenic source, only sugarcane, this case.
Yeah, that actually look like a mix of synthetic ethanol made from petroleum. That's about 30%. And the rest is bio. I don't know, whatever, it's some grasses or corn, whatever was used for fermentation. Yeah, and actually in Brazil it was not a single case, because when they have low crop on corn, they made it from petroleum and say it's biofuel. And your radiocarbon technique can help to... Yeah, Walter.
In Brazil.
I don't know what the worldwide situation is in this. Are there any countries who have already certified places to determine whether the fuel is or biofuel is, what the percentage of biofuel is, and so forth? Is there anything like that going on, or what is the situation in your country?
In Brazil now we have a lot of incentive to produce this type of product, not only biofuels but bioplastic too. The problem is we don't have an entity to inspect this product, so I can produce biofuel and say, this is 100% biogenic. But how can I prove this? I don't inspect, I don't monitor this process. So we don't have yet approved lab to certify this type of product. There's a problem, big problem in Brazil, and try help the government to prove this scenario. Is a big problem, but I believe it's.
Okay.
One more question.
I have a comment, maybe. This 70% that you're worried is a mixture of modern and old. Can you make a biofuel with algae? If you have a
they're cheating with that. They make it from petroleum and add to the gasoline, say 10% of biofuel there.
Instead using corn and algae, which the algae will be modern, but with reservoir age.
No, petroleum ethanol may be even cheaper than plant ethanol, you know?
I would like to comment what Walter was asking. We are doing here, in Italy at least, this is what we are doing here in our lab. We are measuring biofuels on a routine basis, mainly for different Italian petrol companies, mainly for kerosene for aircrafts. The problem is that usually the bio concentration is quite low, and this, you have some more problems in correction for background because you have 1-2% or even lower bio concentration, and this raises some problem in the calculations. But we are doing it on quite routine basis.
Okay. Any more questions? Thank you.
Thank you so much.
Yeah.
I think so. That looks like my presentation. So. What's Monty? Are we having a break or? I'm not sure. We could.
Hello? The other one. Hello? Can you hear me? Yeah? Okay. So we have Monty Ochocki, who's going to talk. Sorry. Can you hear me now? So we have Monty Ochocki, who's going to talk to us about a pre-treatment technique, acid-base acid with step combustion.
Thank you. Hello, everyone. Thanks for having me here. It's great to be here in LECCE. I'm going to be presenting some experiments that were completed kind of as a side project to my PhD, which I finished about 18 months ago, and since then I've been working as a chemistry technician at the Radiocarbon lab in Oxford. And the experiment I'm going to be presenting is focusing on the radiocarbon dating of charcoal. My background is in archaeology and environmental science. Yeah, this, as I said, this is a sort of a smaller project of my PhD. So, as everyone in the room probably knows, charcoal, since the invention of radiocarbon dating, has been recognized as an excellent material for dating. Has a very high carbon content and is relatively stable post-deposition archaeological and environmental contexts, particularly in comparison to other materials like bone or wood. So quite often where dating those materials fails, charcoal might succeed. And as I said, it's frequently recovered in archaeological and environmental contexts. So it's sort of ubiquitous. And it's also terrestrial in origin, so it doesn't sort of suffer from the complications of reservoir effects. But despite all those kind of qualities, it's not immune to contamination or exogenous carbon being included in the material. It's very porous with a high internal and external surface area, and so is susceptible to contaminants from groundwater table movement or microbial activity. And so for that reason, we typically pre-treat charcoal in Oxford. We use these two methods. On the left is the ADA, so acid-base acid wash. The first acid wash is to remove carbonates from sediment-derived carbonates. The base wash then targets sort of loosely bound organic compounds, we might call humics. And then the final acid wash is intended to remove any CO2 absorbed during the previous base step. This is probably all very familiar, but I thought I'd just sort of cover it anyway. And so for older charcoals, we use this method ABOX SC, which stands for acid, base, oxidation, and step combustion. And generally we apply this ABOX method to charcoals suspected to be older than 25,000 radiocarbon years old, or charcoals that are heavily contaminated. And in general, the ABOX method is a more aggressive pre-treatment. And so comparing the two methods, over the last sort of 15 years, there's been a number of studies comparing these two methods and showing that ABOX can be in certain contexts more effective. So this is a figure in the black is ABA dates. In the grey bar down the middle is a known age tephra, and the grey are ABOX dates, and so each sort of row is a single paired dates for those samples, and these are all found below the tephra layer. So what this figure shows is that the ABOX dates are generally in better agreement with that tephra layer. So sort of unpacking those differences a bit further, I can identify three differences between ABA and ABOX. The first is an increase of acid and base wash concentrations, quite a stark increase. This oxidation step using acidified potassium dichromate, replacing the last acid wash in ABA. And then also this step combustion step after wet chemistry. And so in thinking about why the ABOX might be a more effective pre-treatment for these older charcoals, there could be sort of three reasons here, and they could also be interacting. So you might also ask, why not just use ABOX all the time? And one reason not to is that it involves this potassium dichromate, which is hazardous in many ways and sort of looks hazardous as well, and is a bit laborious to work with in the lab. And so one of the motivations in the experiment I'm presenting here was to see if we could sort of avoid using this chemical in future. And some other downsides of ABOX are that generally we need a higher starting mass, a high amount of charcoal, so, which is not always possible. Also, it has a very high sample failure rate overall, particularly during the strong or high concentration base wash. as I mentioned before, the potassium dichromate is difficult to work with, and it's generally more involved, so we only are working on 5 to 10 samples at once, meaning we generally have a lower throughput with ABOX. So the sort of fairly straightforward experiment I designed was to investigate particularly this step combustion step, which is quite similar to the ramped oxidation methods that were mentioned earlier today. And one of the papers that kind of inspired this experiment or sort of motivated it was here, showing that perhaps ABA-SC for these 3 samples here can produce ages similar to ABOX-SC. So perhaps suggesting that the step combustion stage of ABOX is the sort of important part. So the samples are sort of selected from the Radiocarbon archive in Oxford were previously shown to have these differences between ABA and ABOX dates. And they're from a site in the north of Italy called Fumani. And these blue stars here are on the stratigraphic diagram are where the samples came from. And these are upper Paleolithic or middle to upper Paleolithic layers, so at the sort of transition there. And this paper at the top is the sort of paper that showed these differences for these charcoal at Fumani. So here's a table of those differences. And just to sort of reiterate the basic idea, on the left here are the ABA dates, on the right are the ABOX dates, and the idea is to sort of take these ABA excess pre-treated material, apply a step combustion step to it, and then compare those dates to the ABOX dates. And the step combustion method in Oxford looks like this. So we take around 20 milligrams of freeze-dried ABA-treated charcoal for this experiment, put it in a crimped combustion tube, plug the tube with silica wool, evacuate the tube, add 600 millibar oxygen, and then heat to 630 degrees. So, and then after this, the remaining material we combust and graphitize in the routine way. So here, looking at the results of this experiment, so I should say as well the ABA dates were repeated to sort of account for any differences between their original dates. Some of these samples had been in storage for about 20 years, and so we repeated the ABA dates. So the x-axis here on the larger plot, each column is a separate sample, and in red, blue, and green are the ABA, ABA-SC, and ABOX-SC dates. And consistently, the ABA-SC dates are older than ABA, but younger than the ABOX-SC dates. And so in general, that suggests that the sort of wet chemistry of ABOX is also an important factor, at least in this, in the context of Fumani. And then as a way to sort of compare these dates and give them a kind of common method to compare between them, this is a sort of measuring the proportional effect of step combustion on this ABA material expressed as a proportion of the inferred contaminant removal by ABOX. So if the ABA-SC date was the same, we'd see a value of 1. And so the dotted line is a mean of these values, and tentatively suggests that step combustion in this case can account for about 50% of the contamination removal by ABOX-SC, but there is some variability there as well. And then on the bottom is stabilized values, which aren't terribly consistent, but in most cases suggest enrichment after step combustion. And as I said, there was also this sort of opportunity to test the effect of up to 20 years in storage, or 27 years in storage. And in general, there was no consistent pattern between the ABA dates that we measured. Only one surpassed the chi-squared threshold we use to sort of highlight differences between radiocarbon dates, and that was the sample that had been in the archive for the longest. And the stable isotope results were remarkably consistent. And so the conclusions, as I said, step combustion has a significant effect in contaminant removal. We do see a difference in the dates after step combustion of ABA material. Our long-term storage didn't show any consistent pattern, which was good news. And I guess less good news is that potassium dichromate is important, or at least and/or increased acid and base concentrations are shown to be important. So we'll carry on. And in future, I would say it's still unclear why ABOX is producing sort of producing these older dates in certain contexts. I think it would be useful, as in some other papers, to use elemental analyses or FTIR along the way to understand what's being removed, how the material is changing along the way. And also, in the case of Fumani, these were unknown age samples. And so there are examples of known age samples, or another method would be to sort of spike the samples, contaminate them with a known contaminant. So, yeah. And volare.
Thank you very much. Very impressive indeed.
Just have to go for it.
Questions?
Okay. Thanks for the interesting talk. I might miss your view, but the thing is, when you look at the delta C carbon 13, most of the case when you have the younger, the older age, you have the lower or higher delta C carbon 13, right? What does it mean?
Delta 13C.
Yeah, what does it mean for? Does mean the contamination have a lower delta C carbon 13? What does it mean there?
I mean, this general pattern would indicate, I would say, a sort of preferential combustion during step combustion of the lighter material. It might suggest as well that a sort of separate fraction is being removed during the step combustion.
Does it point out, what kind of contamination because you have lower delta C carbon 13?
The contaminant has a separate delta 13C signal, you mean?
I just wonder, what the meaning for low carbon, that's mean contamination from a lower carbon 13 compared to the real age, right? Yeah.
Yeah.
Okay. I just wonder, what it mean into the environment,
Yeah, they're not sure. I might have a separate, here is some sort of more detailed data on the step combustion. We also see a much higher carbon content after step combustion, a reduction in mass overall. So it's certainly changing the material, but as to how or exactly what's happening.
I wonder why you chose 630 degrees. That's first part. And second, why you call it step combustion? Because you have only one temperature. Friendly question.
Yeah. So it's the sort of stepped combustion method refers to the sort of original design of the ABOX SC method, which I think was 1999 it was sort of developed. In those experiments, there were 3 temperature steps. In the lab, we sort of disregard the first temperature step, so that I think it was 400, 600, 900. So we don't do the 400 step. We step combust the material at 630 degrees, and then effectively the last step we do by the routine combustion at 900 or 1,000 degrees.
So you do 2 temperatures, therefore.
2 temperatures.
I see.
Yeah,
Okay.
yeah,
Gotcha. Yeah.
As far as I know, Tom Hyam has corrected some of his earlier measurements in connection with the Neanderthal to older and older ages. So the question is, do we have to believe that the older ages are the more correct one now? Is the or can we not do this? Can we not conclude this yet?
Yeah, as I say, the sort of downside of this experiment is that the Fumani samples are not known age, and and there's no tephra at the site that's been found yet that can confirm that. So I guess the kind of confirmation of the ABOX states in this case were given by comparison to dates on bone. So there was a kind of, I guess it's sort of independent method by comparison there. But I do appreciate your point as well that it doesn't necessarily mean that, sort of older is improved contaminant removal. Yeah.
Thank you.
One more.
Thank you. You said you lose about 50% of samples if you apply high concentration sodium hydroxide or whatever base you use. Did you try to avoid this step and after acid treatment to do oxidation?
So there are some other experiments, and I believe are unpublished at the moment, that were missing the base step, so AOX, and the downside there is still that the potassium dichromate needs to be used in the lab, so the sort of motivation for this was to find a simpler method. But if I can sort of cycle back to those 3 differences, really exploring these differences between ABNA and ABOX could quickly kind of scale out into quite a big experiment. And there's also the other variable of where the samples come from and the different environmental contexts that they could be from. So I sort of chose to focus just on this one aspect.
I'm asking because potassium dichromate will oxidize humic acid, which is actually you try to extract with base. And maybe it will preserve your samples. I don't know. I just asking if you try to do this.
It's definitely the base step where most samples are lost. In ABA as well.
Okay, thank you.
Very, very, very short.
First is a comment. Your ABA treatment seems a little bit weak. The base is very weak, so it seems a little bit unfair compared with the A-box step combustion. I'm familiar with the A-box because I worked with Michael Bird before, exactly with this treatment. And the second thing is blink correction is important in terms of sample processing. So you didn't mention any blink for your correction. So can you comment on that very briefly then?
Yeah, we did sort of routinely use background charcoals, and I didn't show that data. I did the same as went to the archive, got the already ABA treated material and dated those as well, and we saw no change. So I didn't include those as a. I thought it would sort of complicate things because we didn't see any difference between these things. But yeah, we sort of processed the standard in the same way alongside these things.
Thank you very much, Monty. So next talk, Kai Nakajima, who's going to talk to us about flow cytometry.
So, okay, thank you. So, I'm going to talk about pollen separation. So, I'm interested in dating pollen, specifically pollen extracted from lake sediments, and I'm going to show you how flow cytometry can be used to do this. Pardon? Hello? No, sorry. So, I'm interested in dating pollen, specifically pollen extracted from lake sediments, using a technique called flow cytometry, which is a relatively well-established technique, originally in the medical sciences, but now slowly finding its way into the earth sciences. So the problem with radiocarbon dating lake sediments is that the carbon found in sediments comes from various components of the carbon cycle, which all may be characterized by their unique 14C signature and their history of transport and recycling processes. So we have a lot of pre-aged organic carbon in lake sediments, as well as those marked by reservoir effects or hard water effects. And a solution to this is to target a specific component of this of the sedimentary matrix, and the most straightforward way is to do this with macrofossils, usually from terrestrial plants, but the macrofossils are often too scarce, so chronologies reliant on them are often too unreliable. So people early on suggested that pollen are maybe the ideal alternative to macrofossils. So pollen, which you can see here, are usually well preserved. They are composed of a polymer that's chemically very inert, and you can find them practically everywhere. They come in various shapes and sizes, but typically one pollen grain constitutes around 1 nanogram of carbon, so you need a lot of them for radiocarbon dating. At the same time, they are established markers for past vegetation coverage. So if you can get a radiocarbon date on pollen, you can get a proxy-specific and source-specific chronology. So traditional approaches for extracting them have proved to be not suitable for it, mostly because they are either too time-consuming or don't achieve the purity. And flow cytometry can overcome these issues. So this is the general workflow. So first we do some chemical pre-processing. We take around 1 gram of dry sediment treated with hydrochloric acid, sodium hydroxide, and hydrofluoric acid in order to remove carbonates, humic matter, and silicates. This results in a particle mixture of organic debris, which is still dominated by other particle types. We take this particle mixture and introduce it into a flow cytometer. So this flow cytometer takes suspended particles and focuses them into a stream of microdroplets, and a laser analyzes each particle individually for its optical properties, and when these optical properties meet predefined criteria, a charge is applied to this droplet and it gets deflected into collection tubes. So with this step, we are removing all the other organic particles, and we are left with a sample that's practically composed of only pollen. So we take this sample then for combustion into an EA-coupled AMS system, but also because we are dealing with relatively small sample sizes of around several tens of micrograms of carbon, we need to do some blank corrections. So during flow cytometry, we are analyzing around 1,000 particles per second, and we are analyzing for forward scatter, side scatter, and 2 different fluorescence intensities that are emitted after excitation with the laser. And these properties reflect the particle size and surface complexity as well as its molecular composition. So we can define the areas in the parameter space that's dominated by pollen. So in blue and red, these are the regions in the parameter space dominated by pollen, and all the particles that are in both regions are getting deflected and for collection. Usually, sorting recovery is around 80% or higher, and we can balance the sorting purity with the duration of the sort. However, differentiation between different pollen species is not possible because there's too much of an overlap between pollen of different plant species, and there's no clear boundary between pollen and other particle types. So in practice, if you take a pre-processed pollen sample which has like around 1% of pollen concentration, and we want to extract 50,000 pollen, then this results in a sample of around 50 micrograms carbon, and in the highest purity setting, it takes around 10 hours of sorting. So here you see a comparison of before and after flow cytometry. So on the left side, just the pre-processing, we have a lot of plant debris, and other organic debris, and pollen account around 5% or less of the entire of all the particles. And after the sorting, we have like pollen purity of around 95% or higher. Purity in terms of carbon mass might be even higher than this. So because of the small sample sizes, we have to do a blind correction, and for the blank assessment, we've included processing standards alongside normal part samples for the entire procedure. So here we are tracing the fossil contamination with modern pollen. Each color represents a different processing batch from which I've subsampled several samples with the flow cytometer. So I've done the same with carbon dead pollen as well for tracing the modern contamination, and in total we get around 1.34 micrograms of carbon constant contamination, regardless of the sample size or the batch. And this data we can now use to correct all the 14C data of our actual pollen samples. So here I compare how our pollen 14C dates perform against tephra dates of known ages. So in blue you see the reference ages from the literature for tephra events from tephra layers of volcanic events across 10,000 to 13,000 years ago, and I sampled 2 centimeters of sediment around each tephra layer. So you see in the tephra, our pollen dates in gray, and the match for the oldest 3 samples from the very top to the match is quite good. Even for the last one, it may not look like it, but the age estimates just are barely touching at the 2 sigma intervals, but there's a good agreement within the 3 sigma intervals. Unfortunately, because of how the calibration curve is shaped during this time interval, it doesn't allow us to really determine whether our pollen age is actually older than the reference tephra age or not. So for the next record, I compare the pollen dates against macrofossil 14C data and TOC for a lake record located in Sweden. And here we see that pollen, macrofossils, and TOC generally follow the same line with some age offset. If you look closer to it, so now the difference in radiocarbon ages between macrofossils and TOC and pollen and macrofossils, we see that in red, the TOC is systematically older by around 300 radiocarbon years. Makes sense. For the pollen, however, we see a huge variety actually in the age difference between pollen and macrofossils. And for some, there is practically no difference. The match is perfect. And for some, they are like barely overlapping within the 3 sigma intervals. And so if you look on average, the pollen are around 150 radiocarbon years older than the macrofossil counterparts. And the most plausible explanation we have for this is that pollen are getting resuspended within the sediments within the lake by events such as winds, and they are resettling above the less mobile macrofossil counterparts, which then accumulates it into an age bias between those 2 radiocarbon targets. And one of the reasons why we think this is the best solutions, the best explanation is that for the oldest part where we have a really good match between pollen and macrofossils, the sediment is composed of primarily clay, whereas for the rest of the record, it's composed of detrital getter, which is more prone to resuspension than clay. So we think that sedimentary processes may be a cause for an offset between macrofossils and pollen. So in summary, I've shown you that flow cytometry can be used for separation of pollen, and we can achieve quite a good separation with very low contamination actually. So we can measure pollen sample sizes of around 20 to 30 micrograms. Pollen data that we get are generally in agreement with tephra and macrofossils, but at the same time we see in some instances offsets between macrofossils and tephra, which may reflect delays between the formation of pollen and their final deposition in lakes. So this was only one example of how flow cytometry can be applied, and there's a huge variety and open research field for how this could be used for other particle types such as coccoliths, algae, and spores, and other other particle matrices such as suspended particles or sediment trap samples worked as well. So if you're interested, come see my poster on coccolith 14C analysis tomorrow, and thank you very much for your attention.
Thank you very much. Are there questions from the floor?
Two questions. One, which suspension fluid did you use, or solution, when you do the flow cytometry? And the second is, any reason why aquatic pollen, since you're doing lake sediments, should not give some older ages? Because you say you cannot sort.
Yes. So in this case, they're just first the fluid. So it's practically milky water, only milky water, and I add a little bit of sodium chloride to make them chargeable, because you need to charge the particles, droplets. As for aquatic pollen, so in this case, the pollen record was completely dominated by trees. So that's like the reason, you see. And even for locations where aquatic plants are more present, it's because mostly because aquatic plants do not produce as many pollen as trees. Especially conifers dominate most pollen records, so they don't contribute too much to the final size, and they are also smaller. So, yeah.
Other questions? I have one quick one. So you were saying about the pollen being older to do with perhaps biotibation or resuspension in the lake. But is there a chance that the pollen that's delivered to the lake has been stored in the environment and is aged?
So this was one of the explanations, possible explanations as well. But so one, if pollen were stored in a different compartment in the environment, in the landscape, then you would be able to see it, because they would be more degraded. As for, in this case, pollen were perfectly clean, so we are suspecting it happened like within the water column. Yeah.
Great, thank you. Thank you very much.
Yeah, we have now a small change in the program, because Slava Kuzmin is going to give his talk during this session. Then we have the coffee break, and then for today it's over. Okay? So the last talk will be given by Slava Kuzmin in this session, the last one.
Okay, there we go. Gotcha. What is this? F5 or something? No. Aha, gotcha. Buongiorno. Welcome to Siberia, by the way. So, let's talk a little bit about the mammoths. Yeah. Iconic animals, as you know. That's what it probably looked like. So Mammutus primigenius, so bigger than modern elephant, and they inhabited all, Eurasia, as you know, and more than 200 years of scientific research passed, but still no any serious clue why these giants went extinct. Several kind of hypotheses were proposed: climatic, catastrophic, including extraterrestrial, this whatever young Dryas, bolide or something from the space. Geochemical means suffering of the certain elements at the end of the existence. Anthropogenic, that's human hunting. Infections, some diseases which killed the mammoths. But none of them explain, reliably why they went extinct. Most probably, the most kind of factually based are climatic and anthropogenic hypotheses. Each of course, each has some problems here and some advantages too. Yeah. So we created the database of about 950 direct radiocarbon dates on bone, teeth, and tusks We avoided tissues because they're often contaminated. So of the woolly mammoths from Siberia and Russian Far East. So, and then we try to understand, first of all, the spatio-temporal distribution, although it was done before, but anyway, that's some updated. And then its relationship to climatic changes, climatic fluctuations, in the last 50,000 C14 years. Yeah. So here's the distribution of direct radiocarbon dates on woolly mammoths from Siberia. As you can see, many dates are concentrated in the north of the region. So that's why people were usually, doing sampling. It doesn't mean that mammoths didn't exist in the central part of Siberia. They did, but less material is available. Yeah. If you see the distribution by latitude, that's the one. So similar to what I showed, about 70% of dates comes from high Arctic, north of 68 degrees northern latitude. In other words, beyond the Arctic Circle. So that's the current situation. We shall take into account, but I think that's not a big problem because area is big and we can still derive some conclusions about spatio-temporal distribution. Okay. So actually we started 20 years ago with dating of the Paleolithic sites and figured out that the average sigma for set of C14 dates is about 500 years. Therefore, plus minus 500 years is about 1,000 years. So we decided to use the 1,000 years increment. So to plot the distribution of dates. So as you can see, the fluctuations is quite big. And what is interesting, does it work or not? Anyway, just see the very high number, 31 dates between 11 and 12,000 C14 years. That's a Younger Dryas. Just before the mammoths went extinct in a few thousand years, but the amount of them was quite high at the time. Here it is. That's the one. So very high number and then decreased very quickly. And before that it fluctuates, doesn't stay stable, but the small number in the beginning is just because we have less older samples, not just means there were less mammoths, just a degree of study. All right, so that's a distribution. Maybe it is. Yeah. So what we can say that until 12,000 radiocarbon years, mammoths existed throughout Siberia. And after that, very few refugia south of 60 degrees north we have, between 12 and 10,700. And at that time, mammoths populated mostly northern part of the mainland, Arctic, until 9,700. And after that, they existed only in what today are islands. Perhaps some of them were not islands due to the post-glacial sea level rise, but right now they're New Siberia Islands and Wrangel Island. So that's what do we have today after 9,500, so early Holocene, middle Holocene. Here's just last glacial maximum and soon after that. You could see that mammoth southern limit was quite far south. So, okay, going closer to the modern time, these red circles represent some isolated or semi-isolated occurrences of mammoths, which you actually do not call refugia, it's just south of 60 degrees north. But again, in the north, there are more dates. But when you come closer to the beginning of Holocene or Younger Dryas, you can see only one refugium That's in 55 degrees north in the southern Siberia. The rest are beyond the Arctic Circle. Taimyr Peninsula, Yamal, and the islands. So that's a real break of the mammoth habitat. And Volchagriva, we are pretty certain we have like 40 C14 dates on this site, and that's the youngest one. So we are pretty certain that's a definite refugium. Why refugium? Because, as I think, from Eastern Europe and Central Europe, we have a few refugia like this too. I think at that time, the mammoth landscape still survived, like a, grass-dominated steppe landscapes and patches. They still existed, but very fragmentary. That's why mammoths were able to sustain in some of them. But in the rest, it's just, forest derived and bogs, and that's no mammoth habitat, no grass, dry grasslands, and that's it. So the last time of mammoth existence, the last stages, that's from 10,000 to 8,000, very, very high north, a few in the mainlands, but mostly in the islands, and that's the last stand of mammoths, well known in Wrangel Island in the high Arctic until 3600 BP. Well, that's the dynamic of mammoth disappearance. Another aspect is relationship between dynamics of mammoth population fluctuations and climatic changes. So, turned out, as some people were saying, it's not linear, it's not straightforward relationship. And we used the study by Puzachenko and others published some years ago, and we just took only Siberian part of their database, and we added our new dates which they didn't have. So what we did, we calculated so-called average accumulating rate for each major climatic events, either cold or warm. I'll show you in a second. Normalized for 1,000 year intervals, because some of these stadials, interstadials, they have different lengths, so we have to normalize it. So that's what we did, and that's Muskovitz, Puzachenko, a group from Moscow, they did the same. But they have less for Siberia, but more for the rest of Eurasia. So here, the yellow are interstadials, warmer, like Moishort, Hengelo, Dennenkamp, Berlin-Kalleröd, last glacial transition after LGM, and then, of course, early Holocene. And the blue ones are stadials, like last glacial maximum, Younger Dryas, and a few others, established using the mostly palynological data. And this dotted line, that's a very schematic representation of the delta oxygen 18. So again, for each major climatic event, we plotted the delta oxygen 18 just to see the correspondence. And then try to figure out, is there any trends or any correlation between them? So which turned out to be tricky. But anyway, so from the first glance, you could see that usually the number of these occurrences of mammoths for cold and warm intervals, it's not very different from each other. Before 12,000 calibrated, before the Younger Dryas. And after Younger Dryas, the mammoth quickly disappeared, and it's all related to the warming. Yeah. So cooling after 12,000, practically no cold stage after Younger Dryas. So, but otherwise, warm and cold, it's pretty similar number, yeah. With some fluctuations, of course. What we are thinking that there is no direct correlation between number of mammoths and the oxygen, delta oxygen 18, which is a kind of temperature trend. Yeah? So what we tried to apply the trend analysis. And we arrived to the preliminary conclusion that the trend is a clear second-order dependence, which is a polynomial, which shows increase in number of occurrences during climatic coolings. And then, so although we have some very high number of occurrences, and try to remove it, considering maybe it's anomalies, but when we got rid of them, it still doesn't change picture much. I'll show you in a second. So the blue, that's the total set of our dates. And you see the R square is 0.82, good number. And these blue ones, which were thinking maybe outliers, okay, we deleted them, and the correspondence even better, 0.92. But if you can project this trend further, it's still this blue stuff will still be on the same line or so. So it's not real outliers. So, but still we did two kinds of, analysis. And then, so the result is this, that the trend consists of two parts. First, the more mammoth means colder intervals. And then the trend changed. The more mammoth belongs to the warmer intervals, which means that the relationship is non-linear. It's just more complicated, and more work is needed to understand, in details and try to different, models of correlation, correspondence, and so on and so forth. But I'm pretty sure that it was not simple model like it's getting cooler, there are more mammoths, it's getting warmer, there are less mammoths. No. That situation was very different from such a linear thinking. But, well, we are trying to get more information, and that's what just the first results we presented here. Well, any clues why mammoths went extinct? Do you have any? Please, give me advice. Thank you. Grazie mille.
Thank you very much. Questions?
How sure are you that they are extinct completely?
Well, some native people in Siberia still believe they exist. Yeah.
Okay.
Well, we didn't see any living one for what? 300 years or 400 years of Russian, colonization, so, of course.
Slava, you show the data on the mammoth, and you connect to Delta 18. What about the distribution of human, distribution of forest, as you say, the
right.
driven, and put the time, like how long does it take to build a forest? And, we are talking about the natural environment and not...
Yeah, good question, yes. I didn't pay attention in this presentation because of the time kind of limit. But first of all, humans settled the northern Siberia very late. The only one site dated back to 28,000, the only one. The rest are 10, 15,000 only. Wrangel Island, the first humans appear 500 years after mammoth went extinct. So they didn't overlap. Forests usually in Siberia start to dominate at the end of the Younger Dryas, early Holocene. So deforestation started in the early Holocene, in other words. But again, as I showed this Volchagriva in central Siberia, it's still forest steppe right now, with a lot of steppes. And probably there was a patch of steppe surrounded by forests or something. Not a taiga, but like a mixture of conifers and deciduous trees. So, but doesn't look like there's a straight correlation between appearance of forests and the disappearance of mammoths. We actually had a paper in Nature Communications with Glenn MacDonald 2012 where they put his part of from UCLA put the all this forest data, appearance of trees and so on, not only mammoths but also bisons and other extinct species. They didn't see any precise trends. But of course, yes, forestation was important because mammoths couldn't exist in the forest here. But again, it comes quite late in Siberia, and humans even later. And what is important, we have in Siberia and Far Eastern Russia, it's 14 million square kilometers, okay? It's double size of the 48 United States. Huge territory, yeah. But we have only 1 or 2 direct evidence of mammoth hunting. Means the holes in mammoth bones, made by spears and so on, extremely few. So extremely few. The mammoth hunting in Siberia didn't affect, seriously the, whatever, existence of a population. Very little. The same in Central Eastern Europe. Very few direct evidence. Probably they did, killing some old animals or young or ones which were trapped in the mud or something like that. So human role is, I think, negligible. Climate, yes, more important. But how? That's not an easy question. We are working on it.
If they became extinct because of climate warming, how did they survive the previous interglacial then?
Excellent question. That was asked many times by others, because the last interglacial, Aegean in Europe, they somehow survived. Some people say they retreated during Aegean to some refugee alike, and then they spread back. But no, I don't think it was. In Siberia, again, it's very conservative region in terms of vegetation. It's huge continental, not many oceans and seas around. Climate is, dry and cold in, winter, very hot in summer. That's why probably the landscapes didn't change dramatically during Aegean in central Siberia, for example, like Yakutia today. Yeah? That's why they felt pretty cozy there. In maritime regions like Western Europe, of course, the climatic warming affected much more the vegetation and habitats of big animals. Yeah. So still, this question was not answered. Yeah, why they survived? Mammoths appeared, woolly mammoths, about 600, 700, 800,000 years ago as a species. So it survived several interglacials. Yes, indeed. Yeah, big question. I agree. Yeah, Alexander. Yeah.
Can they survive in the forests?
No, I don't think so.
No.
They were, according to what we found in the stomachs, of mammoths, they were eating mostly grass and shrubs.
Yeah, it's called tundra steppe.
Yes, tundra steppe, or whatever. Yeah.
But you have a big peak of mammoths when, in actually, what it's called, Wisconsin warming, with 22, 30, I'm sorry, 29, 32. That was actually some interstitial, which was much warmer.
Yeah.
Maybe even warmer than we have now.
I see. You mean during the deglaciation?
Yeah, but you have a lot of mammoths. I don't know exactly where they come from.
Yeah.
It does not say it. From South Siberia or Northern.
I understand. We can separate it. Yes, well, the number fluctuates, but that's not a very significant, yes, there are more, but that doesn't mean they felt better, the environment was better for them than previously. So my idea was try to compare it with the, Greenland ice cores, but there are much more details, Greenland ice cores. And we can, if we will do it, it's just would be, I think, monkey business, So you have to take the larger climatic units, climatic events in the past. Because, there's 50 years or so resolution for Greenland ice cores and 1,000 for mammoths, incompatible.
Okay, Thank you very much.
You're welcome.
And please join me in thanking all of the speakers for this session before coffee.